Rows of golden cookies glide past, whirring machines, as rich creams and nutty fillings are layered with perfect precision. From the snap of a freshly baked Oreo to the buttery crumble of Chips Ahoy and the smooth peanut punch of Nutter Butter, each treat is a masterpiece of flavor and engineering. Today, we uncover the intricate baking and packaging secrets that bring these beloved cookies from oven to shelf. The process begins with the sourcing and inspection of raw materials, which arrive at Oreo production facilities in bulk shipments. The chocolate wafers require a formulation based primarily on wheat flour, sugar, cocoa powder, palm or canola oil, baking soda or ammonium bicarbonate, lecithin, salt, and natural or artificial flavors, such as vanillin. These ingredients are delivered in separate sealed containers or food-grade silos. Wheat flour, for example, is transported pneumatically into on-site flour silos, where it is tested for protein content, particle size, and moisture levels using near-infrared spectroscopy. Sugar and cocoa powder are stored in bulk bins with moisture controls, while oils are maintained in heated tanks to preserve fluidity. The cream filling, perhaps the most beloved component of the Oreo, is made from a blend of powdered sugar, hydrogenated vegetable oils, emulsifiers, flavorings, and sometimes lecithin. The standard vanilla cream uses vanillin or other flavoring agents, while specialty versions incorporate chocolate, peanut butter, mint, or fruit flavors. All cream ingredients are subject to rigorous quality control procedures before being released to the processing area. These controls ensure the filling remains smooth, spreadable, and stable under varying temperatures and packaging conditions. Once the ingredients pass inspection, the Oreo production process enters the mixing phase. The chocolate cookie dough is prepared first in massive horizontal mixers, often planetary or Z-arm varieties, that can handle hundreds of kilograms per batch. Flour, sugar, cocoa, leavening agents, and other dry ingredients are added to the mixer in exact amounts via automated dispensing systems. Liquid components like oil or water are injected through temperature-controlled piping systems. The mixing process takes several minutes and is carefully monitored to achieve the desired consistency, firm yet pliable. The dough is evaluated for moisture content, texture, and temperature before proceeding to the next stage. After mixing, the dough is conveyed to a continuous sheet forming line. This is where the familiar Oreo shape begins to emerge. The dough is fed into a hopper above a rotary molder or a rotary die cutting machine. This machine presses the dough onto a continuously moving stainless steel belt, forming a thin, uniform sheet. A rotary die cylinder, engraved with the Oreo's iconic floral and branding design, presses into the dough with calibrated pressure, cutting out individual wafers while embossing each one with precision. The scrap dough is immediately separated, collected, and rerouted back into the hopper for reuse to eliminate waste. The formed cookies are spaced evenly on a wire mesh conveyor that carries them into a long tunnel oven. These ovens, often over 100 feet in length, use multiple temperature zones, each carefully regulated to optimize baking. The process begins with a gradual heat increase to activate the leavening agents, followed by higher temperatures to drive moisture reduction and crisp the wafer. Conveyor speeds, air velocity, and humidity are all precisely managed to ensure uniform baking across all cookies. Internal sensors measure the cookie's temperature and moisture content as they pass through each zone, making real-time adjustments to the oven parameters if needed. After baking, the cookies exit the oven and travel through a series of cooling conveyors. Forced air cooling systems reduce the temperature of the wafers to below 30 degrees Celsius, preparing them for the sandwiching process. Any residual heat would melt the cream filling, so this cooling stage is critical. Optical scanners and high-speed cameras monitor the surface of each cookie for cracks, discoloration, or warping. Defective cookies are automatically diverted from the line using pneumatic ejectors. Next comes the cream deposition and sandwiching phase, a marvel of confectionery automation. Cookies arrive at the sandwiching station in perfect alignment thanks to vibratory feeders and orientation systems that flip and arrange them face up. Meanwhile, the creme filling is prepared in a separate temperature-controlled holding tank and pumped through jacketed pipes to the depositor heads. These heads apply a precise dollop of cream onto one side of each wafer using servo-driven pistons or rotary depositors. Immediately after the cream is applied, a second cookie is placed on top to create the signature Oreo sandwich. This alignment is performed by a series of timing belts and robotic arms that synchronize the top wafer's placement with the bottom. Sensors verify that each sandwich has the correct height and fill ratio. Depending on the product line, the amount of cream can be varied. For example, double-stuffed Oreos receive nearly twice the standard filling volume through an adjustable depositor program. The completed Oreo sandwiches now travel to the packaging line via a network of conveyors that may include stacking units, alignment modules, and accumulation tables. Before packaging, each cookie is once again scanned for defects. Optical systems detect broken cookies, misaligned sandwiches, or missing cream. Any rejected cookies are automatically diverted and collected for use in secondary products or disposed of according to safety protocols. Once quality checked, the cookies are grouped into the appropriate quantity per package, often 12 to 18 cookies depending on the product size and region. Packaging formats vary. Traditional flow-wrapped trays, resealable pouches, on-the-go packs, or even novelty containers for seasonal promotions. The cookies are typically placed into thermoformed plastic trays that hold each sandwich upright and prevent breakage during transit. These trays are loaded into pre-printed film sleeves or bags using automated loaders. Flow wrapping machines use heat and pressure to create hermetic seals along the film edges, ensuring the cookies stay fresh. Packaging equipment is calibrated to align the printed design perfectly with the package seams, maintaining brand consistency. After sealing, each pack receives a date code, lot number, and quality assurance stamp via thermal inkjet printers. Some factories also include RFID tags or scannable barcodes for inventory tracking. Chips Ahoy may appear to be a simple chocolate chip cookie, but behind each crunchy bite is one of the most sophisticated and high-capacity food manufacturing processes in the snack industry. As a flagship brand in the world of packaged cookies, Chips Ahoy has been mass-produced for decades, evolving into a highly automated and meticulously engineered operation designed to deliver consistent flavor, texture, and appearance in every single cookie. From the blending of dry ingredients to the precision-controlled baking tunnels and advanced packaging lines, the industrial production of Chips Ahoy cookies is a seamless integration of food science, mechanical engineering, and automation. The story begins long before any dough is mixed, with the sourcing and inspection of high-quality raw ingredients. At the heart of every Chips Ahoy cookie is a mixture of enriched wheat flour, sugar, semi-sweet chocolate chips, palm or canola oil, brown sugar, leavening agents like baking soda, salt, and natural or artificial flavorings such as vanilla. Each of these components arrives at the production facility in bulk shipments. Wheat flour, the base of the dough, is delivered in silo trucks and stored in large indoor silos with humidity and temperature controls to preserve grain quality. The flour is tested for protein content, ash level, and moisture percentage using rapid near-infrared spectroscopy. Sugar, both granulated white and dark brown varieties, is stored in enclosed, food-grade bins or silos. Brown sugar, in particular, is prone to hardening due to its moisture content and is kept in temperature-controlled environments to maintain softness. Chocolate chips, one of the most critical elements, are delivered in large bins or tote bags and handled with extreme care to prevent melting, chipping, or fat bloom. These chips are inspected for size uniformity, cocoa solids content, and melting point. Oil, whether palm or canola, is stored in jacketed stainless steel tanks to maintain proper fluidity and prevent rancidity. All ingredients are tracked and catalogued via an integrated inventory management system, ensuring full traceability from supplier to production line. Once the ingredients are cleared for production, the first major stage begins. Dough preparation. Chips Ahoy. Cookie dough is made in large horizontal batch mixers, industrial versions of stand mixers capable of processing over 1,000 pounds of dough at a time. These mixers are equipped with planetary or ribbon-style agitators and connected to automated ingredient feeders that deliver pre-measured amounts of flour, sugar, brown sugar, and oil directly into the mixer. Liquid ingredients, like oil and flavor emulsions, are pumped in via metered nozzles. A separate, pre-hydrated slurry of baking soda and water may be added to ensure even distribution of the leavening agent. Mixing is conducted in carefully timed stages. The dry ingredients are combined first, then the oil and flavorings are added, followed by any moisture balancing liquids. The dough is not overmixed, as that would develop gluten and make the final product tough rather than tender and crumbly. Once the base dough reaches the correct texture, soft but firm enough to hold its shape, chocolate chips are introduced. This is done at the final stage of mixing, using gentle folding action to prevent breaking or melting the chips. Infrared sensors monitor dough temperature to ensure it does not rise above optimal limits, usually around 25 degrees Celsius, which could compromise chip integrity. After mixing, the dough is discharged into stainless steel dough troughs and conveyed to the forming station. Unlike cookies made at home using spoons or scoops, Chips Ahoy. Cookies are formed using high-speed rotary molders or wire-cut forming machines. These machines deposit uniform portions of dough onto a continuous oven band, usually a steel or mesh conveyor belt. The wire-cut method pushes dough through a die cavity and cuts it with a moving wire blade to create identically shaped mounds. Each mound is embedded with visible chocolate chips that must be evenly spaced and partially exposed on the surface. Vision inspection systems with high-resolution cameras monitor chip distribution and shape uniformity in real time. Cookies not meeting the standard geometry are diverted from the line before baking. Once formed, the cookies are ready for baking, a stage that plays a critical role in the final texture, flavor, and color. Chips Ahoy. Cookies are baked in long tunnel ovens, often over 100 feet in length, with multiple heating zones. These ovens may use convection, radiant, or hybrid heating to control baking profiles. The oven zones are programmed to gradually increase heat exposure, starting with lower temperatures to allow the cookies to spread, followed by high heat to set the structure and caramelize the sugars on the surface. The entire baking process typically lasts between 6 and 10 minutes, depending on the oven type and cookie size. Precision is key here. Thermocouples and infrared sensors embedded throughout the oven monitor surface and internal cookie temperatures. Moisture sensors measure the humidity of the cookies as they travel through, ensuring the final moisture content falls within a narrow window. This is what gives Chips Ahoy cookies their distinctive crunchy texture without being dry or brittle. If cookies are underbaked, they will be too soft and fail shelf life tests. If overbaked, they will darken excessively and develop bitter notes from over-caramelized sugars. As the cookies exit the oven, they pass through a forced air cooling tunnel. The cooling phase is essential not only for food safety and packaging, but also for preserving the cookie's structural integrity. Hot cookies are fragile and may break or crumble if handled too soon. Airflow velocity, direction, and temperature in the cooling tunnel are optimized to reduce the product temperature below 30 degrees Celsius before handling. During this phase, Cookies are also passed under metal detectors to identify any potential foreign objects introduced during earlier stages. Next comes packaging, and this is where the scale and speed of industrial automation truly shine. First, the cookies are singulated, aligned in neat rows by a series of vibratory lanes and conveyor guides. High-speed robotic pick-and-place arms stack the cookies into groups, typically 8 to 16 cookies per row, depending on the package format. These stacks are loaded into thermoformed plastic trays designed to cradle each cookie and prevent movement during transportation. The trays are then conveyed into horizontal flow wrapping machines, where they are sealed in multi-layer plastic films with high barrier properties to resist moisture and oxygen ingress. The packaging film is fed from large rolls, printed in reverse with the Chips Ahoy branding and nutritional information. As the film unwinds, photo eye sensors detect registration marks to align the print design with the sealing jaws, ensuring logos and text appear in the correct location on every package. The film is folded around the cookie tray, and heat sealing jaws apply pressure and controlled temperature to create a hermetically sealed package. Before packages are boxed, they are scanned for seal integrity using vacuum pressure testers or gas leak detectors. Those that pass are directed to cartoning machines, which automatically fold and glue outer boxes around multiple cookie packs. These cartons are then stacked into master cases using robotic case packers and loaded onto pallets by automated palletizing systems. Pallets are wrapped in stretch film, labeled with barcodes and batch codes, and moved into finished goods storage areas. Throughout this entire process, strict quality control procedures are in place. Cookies are sampled at multiple points on the line and tested for weight, diameter, thickness, bake color, moisture content, and chip distribution. Trained sensory panelists conduct regular taste evaluations, scoring cookies for flavor balance, crunchiness, sweetness, and overall satisfaction. Data from these tests are fed into the plant's digital quality control system, which flags any deviation from established product specifications and initiates corrective action protocols. Finished Chips Ahoy. Cookies are stored in climate-controlled warehouses and distributed via a vast logistics network to grocery stores, vending machines, and online retailers around the world. Shelf life testing ensures that cookies retain their texture and taste for months without degradation. Products are tracked by batch number, enabling full traceability from ingredient source to final sale, in compliance with global food safety standards. The entire Chips Ahoy production system is a masterclass in scalable precision, built to produce hundreds of millions of cookies per year without sacrificing quality. Innovations such as energy-efficient ovens, water-saving cleaning systems, and biodegradable packaging are being implemented to reduce environmental impact. New varieties like Chewy Chips Ahoy, Reese's filled versions, or limited edition flavors are produced using the same base systems with modular adjustments to recipes, die shapes, and depositor settings. Nutter Butter, with its unmistakable peanut-shaped sandwich design and creamy peanut butter filling, stands as one of the most iconic peanut butter cookies in the American snack landscape. Originally introduced by Nabisco in the 1960s, Nutter Butter has maintained its place as a favorite for generations, thanks to its distinct texture, balanced sweetness, and signature roasted peanut flavor. But behind the simple appearance of this nostalgic treat lies a complex and highly automated industrial production process that involves carefully engineered dough formulation, continuous baking systems, precise cream deposition, and synchronized sandwiching, all designed for mass production at high speed without sacrificing quality or consistency. The journey of a Nutter Butter cookie begins with the sourcing and handling of its fundamental ingredients. The cookie component is a peanut-flavored crisp biscuit made from a dry blend of wheat flour, sugar, and ground roasted peanuts, along with leavening agents such as baking soda, salt, emulsifiers like lecithin, and flavor compounds including real peanut extract and vanillin. Vegetable oils, typically palm and canola, are used both in the dough and the filling to control texture and mouthfeel. The creamy center consists of a blend of peanut butter, powdered sugar, oils, and emulsifiers designed to be smooth, stable, and pipeable at production line speeds. All raw ingredients are delivered to the manufacturing facility in bulk. Flour, sugar, and other dry powders are stored in dedicated silos or hopper systems equipped with dust control and moisture monitoring equipment. Roasted peanut meal, a key element in both the dough and the filling, is delivered in sealed food-grade containers and tested for particle size, oil content, and freshness upon arrival. Oils and flavoring compounds are pumped directly into insulated holding tanks connected to the production line through temperature-controlled stainless steel piping. Every ingredient is barcoded, tracked, and subject to detailed quality inspection before use, with parameters like microbial load, aflatoxin presence in peanuts, and moisture levels rigorously monitored to meet food safety and consistency standards. The first major step in Nutter Butter's production is dough mixing. The peanut-flavored cookie dough is prepared in large, high-capacity horizontal mixers, typically Z-blade or Sigma arm models, capable of handling several hundred kilograms of dough per batch. These mixers combine flour, sugar, roasted peanut meal, and chemical leaveners first, ensuring the dry components are evenly distributed. Then, liquid ingredients such as oils and flavor emulsions are added while the mixer operates at a lower speed. The resulting dough must be firm yet pliable, designed to hold its shape during forming while baking into a crisp yet tender texture. Throughout the mixing process, inline sensors monitor dough temperature and consistency, with adjustments made automatically by the plant's centralized control system. Once the dough reaches the correct specifications, it is transferred to the forming line. Unlike round or drop cookies, Nutter Butter's signature peanut shape and textured surface require precision molding technology. A rotary molder is typically used for this purpose. Dough is fed into the hopper of the molder, then pressed onto a moving belt by a rotating drum engraved with the peanut shell pattern. As the drum rotates, it cuts and shapes each cookie half directly onto the conveyor, forming thousands of identical halves per minute. The two halves of each cookie, the top and bottom of the sandwich, are formed separately but identically, and the embossed pattern helps enhance the brand identity while also creating additional surface area to improve baking performance. The formed cookie halves are transferred directly into a continuous tunnel oven via a mesh or solid steel baking belt. These tunnel ovens can extend over 100 feet in length and operate at controlled temperatures that gradually ramp up from the entrance to the exit zones. This progressive bake profile ensures the cookies spread and rise properly before the surface sets and the moisture is driven off. Baking times are typically in the 5 to 8 minute range, with peak temperatures around 200 degrees Celsius. Internal sensors and infrared thermometers constantly monitor cookie temperature, color, and moisture content, sending feedback to the oven's programmable logic controller to make real-time adjustments. As the cookies exit the oven, they move through a cooling tunnel. Forced, ambient, or chilled air is blown across the cookies to bring them below 30 degrees Celsius, preparing them for sandwiching. It is critical that the cookies are fully cooled before cream filling is applied. Any residual heat could soften or destabilize the peanut butter filling. The cooling process also helps to harden the cookie structure, making it robust enough to survive handling, stacking, and packaging without cracking. Meanwhile, the peanut butter filling is prepared in a separate subsystem. This filling must be smooth, creamy, and stable enough to retain shape during sandwiching, but soft enough to flow through depositor nozzles without excessive pressure. The filling is mixed in jacketed tanks using anchor-style agitators that gently blend peanut butter, sugar, oils, and flavorings. The tanks are temperature controlled to maintain the filling at an optimal deposition temperature, usually around 35 to 40 degrees Celsius. This ensures the filling spreads evenly between cookie halves without leaking or oozing after assembly. The sandwiching process is among the most intricate stages in the Nutter Butter production line. Cooled cookie halves are directed into alignment tracks via vibratory feeders and conveyors. The bottom halves of the cookies are routed under a row of cream depositors, precision devices fitted with nozzles that dispense exact portions of filling onto each piece. These depositors are often servo-driven to ensure high accuracy and synchronization with the cookie flow. The filling is applied as a centered dome or spiral, depending on the depositor head design, and is engineered to remain stable during the brief time before the top cookie is applied. The top cookie half is then gently placed onto the filled bottom half using vacuum-assisted robotic arms or timing belts with pickup cups. The two halves are pressed together just enough to spread the filling to the edges without cracking the cookies. Optical sensors and laser height checkers verify that the sandwich height falls within tight tolerances, ensuring consistent texture and appearance across every unit. Completed cookie sandwiches are conveyed towards the packaging area. Before they reach the wrappers, they are subjected to final quality control checks. High-speed vision systems examine each sandwich for alignment or fill placement and pattern clarity. Random samples are pulled for manual inspection, where trained quality control personnel evaluate crispness, cream flavor, cookie to filling ratio, and moisture level. Cookies that pass all checks move on to the final phase, packaging. Nutter Butter cookies are typically packed in plastic trays to prevent damage during shipping and handling. The trays are placed into horizontal form-fill seal machines where they are wrapped in printed plastic film with moisture and oxygen barrier properties. The film is unwound from large rolls and formed into pouches around the trays using heated sealing jaws and rollers. Temperature, pressure, and dwell time of the sealing elements are tightly controlled to create strong, tamper-resistant seals. The packaging lines can run at speeds of several hundred units per minute and include automatic rejection systems for underweight, misaligned, or unsealed packages. Each package is then inkjet printed with a lot code, production date, and best buy information. Ensuring full traceability, packs are sorted into display cartons using robotic case packers, then palletized with precision by automated palletizing arms. Pallets are shrink-wrapped, labeled, and moved to finished goods storage in climate-controlled warehouses. Throughout the facility, data from every part of the production process, from dough moisture to fill weight to oven temperature, is logged and monitored using a centralized SCADA system. Operators and quality engineers can review trends, track deviations, and make immediate process adjustments to prevent off-spec product from reaching the market. This tight integration of process control and automation enables Nutter Butter factories to produce tens of thousands of cookies per hour with minimal variation. In recent years, Nutter Butter production lines have been updated with sustainability goals in mind. Energy-efficient ovens, heat recovery systems, and closed-loop water systems are being implemented to reduce resource usage. Some facilities are experimenting with recyclable film structures for packaging and plant-based alternatives to certain emulsifiers to make the product more environmentally friendly. New product varieties, such as Nutter Butter Bites or fudge-coated Nutter Butters, are produced using modified versions of the same production lines. These require adjustments to depositor heads, conveyor configurations, or coating systems, but benefit from the same precision-oriented process architecture that governs the original sandwich cookie. The packaged Oreos then pass through metal detection and X-ray systems to ensure no foreign objects have made it into the final product. Units that pass inspection are routed to robotic case packers, which load the cookie packs into corrugated boxes. These boxes are sealed, labeled, and palletized by robotic arms with vacuum or gripper end effectors. The completed pallets are shrink-wrapped and transported to finished goods warehouses, where they are stored in climate-controlled conditions. From there, Oreo products are distributed to global markets through a tightly integrated logistics network. The shelf life of Oreos, typically 9 months or more, is maintained through proper temperature and humidity control throughout the supply chain. Logistics software tracks every unit by batch number, enabling traceability from factory to shelf. One of the most remarkable aspects of Oreo production is the ability to maintain uniformity at massive scale. A single production line can produce tens of thousands of cookies per hour, each one identical in taste, texture, and appearance. This level of consistency is made possible through sophisticated control systems, real-time data analytics, and rigorous staff training. Factories are continually investing in upgrades to improve sustainability and reduce environmental impact. Water reclamation systems, energy-efficient ovens, and biodegradable packaging materials are being tested and implemented in various Oreo production facilities. Some lines now incorporate AI-powered predictive maintenance systems that detect signs of wear on mechanical components and notify technicians before failures occur. Oreo's manufacturing process is also adaptable, allowing for the seasonal and regional variations that have become popular with consumers. From limited edition flavors like pumpkin spice or birthday cake to international variants like green tea or dulce de leche, the same core equipment can be reprogrammed to handle new recipes and designs with only minor changeovers. This flexibility, combined with high efficiency and quality control, is what enables the Oreo brand to continue expanding its global presence without compromising on the taste and texture that made it a classic in the first place. The journey begins with sourcing green coffee beans. Factories procure these beans in large quantities from coffee-growing regions such as Brazil, Colombia, Vietnam, and Ethiopia. Since instant coffee requires consistent flavor profiles, manufacturers often blend beans from various regions to create a balanced and standardized flavor. Upon arrival at the factory, the green coffee beans are subjected to rigorous quality control checks. Samples are tested for size, moisture content, and defects to ensure the beans meet the factory's standards for processing. Once approved, the beans are stored in massive silos made of food-grade stainless steel or aluminum to protect them from contamination, pests, and humidity. These silos are equipped with automated systems that precisely dispense beans onto the production line. The first major step in processing the beans is cleaning. Coffee beans, even after being cleaned at their origin, may still contain impurities such as dirt, stones, sticks, or metal fragments. In the factory, the cleaning process involves several stages. Vibrating screens sift the beans to remove large debris, while air classifiers blow away lighter materials like husks or dust. Magnets are used to extract any metallic particles. Some factories also employ optical sorting machines, which use cameras and sensors to identify and remove defective beans or foreign objects. This thorough cleaning ensures that only high-quality beans proceed to the roasting stage. Roasting is a critical step in developing the rich, complex flavors of coffee. Factories use industrial coffee roasters, which can process thousands of pounds of beans per hour. The roasting process is controlled by highly advanced systems that allow operators to customize the roast profile for specific flavor outcomes. For instant coffee, medium to dark roasts are commonly used, as they bring out bold flavors that translate well into the final soluble product. Roasting temperatures typically range between 370 and 540 degrees Fahrenheit, depending on the desired flavor profile. During roasting, the beans undergo the Maillard reaction, a chemical process that creates the characteristic aromas and flavors of coffee. The roasting equipment includes temperature sensors and real-time monitoring systems to ensure uniform roasting across large batches. Once the roasting is complete, the beans are cooled rapidly to stop the roasting process and prevent overcooking. Factories use air cooling systems or water spray cooling, depending on the setup. Cooling is an important step, as improperly cooled beans can lose their flavor or become brittle. After cooling, the beans are sent to grinding machines. The grinding stage reduces the roasted coffee beans into smaller particles, which will be used for the brewing process. Factories use industrial grinders, such as roller mills or hammer mills, capable of producing a consistent grind size. The grind size is crucial because it affects the extraction process that follows. For instant coffee, a relatively coarse grind is typically used to optimize the brewing process in the factory. The ground coffee is then stored in intermediate holding bins, where it is kept fresh until it is ready to be brewed. Brewing is the next major step in instant coffee production, and it is carried out on an industrial scale. Massive brewing systems, similar to oversized percolators, are used to extract the soluble compounds from the ground coffee. These systems consist of large stainless steel extraction tanks or columns, which are designed to hold thousands of gallons of water and coffee grounds. Hot water is circulated through the coffee grounds at precise temperatures and pressures, mimicking the brewing process used at home, but on a much larger scale. Typically, water temperatures range between 190 and 205 degrees Fahrenheit, and the brewing time is carefully controlled to maximize flavor extraction while minimizing bitterness. The brewed coffee concentrate, a liquid containing the extracted soluble compounds, is then filtered to remove the spent coffee grounds. Factories use advanced filtration systems, such as centrifugal separators or fine mesh filters, to ensure that no solid particles remain in the liquid. The spent grounds are often dried and repurposed as fertilizer or biomass fuel, making use of every part of the raw material. At this stage, the coffee concentrate is a highly aromatic liquid, but it is still far from the final product. The challenge is to transform this liquid concentrate into a stable, dry, and soluble form. Factories use one of two main methods for this: spray drying or freeze drying. Spray drying is a fast and cost-effective method that is commonly used to produce instant coffee powder. The coffee concentrate is first preheated to reduce its moisture content. It is then pumped into a tall, spray drying chamber equipped with nozzles that disperse the liquid into fine droplets. At the same time, hot air, typically around 480 degrees Fahrenheit, is blown into the chamber. As the droplets fall through the chamber, the water in the coffee concentrate rapidly evaporates, leaving behind fine coffee powder. Spray drying is efficient and capable of processing large volumes, but the high temperatures can sometimes lead to a slight loss of flavor and aroma. Freeze drying, on the other hand, is a more delicate and sophisticated process that better preserves the natural flavors and aromas of coffee. The coffee concentrate is first frozen at extremely low temperatures, usually around 40 degrees Fahrenheit, to form solid slabs or granules. These frozen coffee pieces are then placed in a vacuum chamber. Inside the chamber, the frozen water in the coffee undergoes sublimation, a process where ice turns directly into vapor without passing through the liquid phase. This method requires precise control of temperature and pressure and takes longer than spray drying, but it produces high-quality granules of instant coffee that dissolve easily in water. After the drying process, the instant coffee is sifted and graded by particle size to ensure uniformity. Any oversized or undersized particles are removed, and the coffee is blended to create a consistent final product. Factories conduct rigorous quality control tests at this stage, including flavor analysis, solubility testing, and moisture content measurement. These tests ensure that the instant coffee meets the desired standards for flavor, aroma, and texture. Packaging is the final step in the production process, and it is designed to protect the coffee from moisture and preserve its freshness. The dried instant coffee is transported to high-speed filling machines, which dispense precise amounts of coffee into jars, tins, or pouches. Factories use nitrogen flushing systems to replace oxygen in the packaging, as oxygen can degrade the coffee over time. The jars are sealed with airtight lids, while pouches are heat-sealed to maintain freshness. After sealing, the packages move to labeling stations, where automated systems apply branding, ingredient lists, and expiration dates. Each package undergoes a final inspection using vision systems to ensure there are no defects in the seals or labels. Once approved, the packages are packed into cartons or cases using robotic packing systems and prepared for shipping. Pallets of instant coffee are stacked and wrapped for stability before being loaded onto trucks or containers for global distribution. Throughout the entire process, factories rely on advanced automation and engineering to ensure efficiency and consistency. Programmable logic controllers and supervisory control and data acquisition systems monitor and control every stage of production, from roasting and brewing to drying and packaging. Real-time data on temperature, pressure, humidity, and other parameters allows operators to make precise adjustments as needed, minimizing waste and ensuring high-quality output. Hygiene and food safety are also paramount in instant coffee production. Production areas are designed with food-grade stainless steel surfaces, seamless flooring, and clean room environments to prevent contamination. Positive air pressure systems are used to keep airborne particles out of critical areas, and employees are required to follow strict hygiene protocols, including wearing protective clothing and adhering to cleaning schedules. Factories are regularly inspected and certified to meet international food safety standards. Inside a tea factory, the transformation of fresh tea leaves into the familiar tea bags, loose leaf tea, or powdered varieties is a carefully orchestrated process. It is a seamless blend of tradition, precision engineering, and science. Every step of the way, from leaf intake to packaging, is designed to preserve the flavor, aroma, and quality that tea enthusiasts have come to expect. While the type of tea being produced, whether black, green, oolong, or white, dictates specific steps in the process, the overall journey is one of meticulous attention to detail, where both manual expertise and advanced machinery play vital roles. The process begins at the tea gardens, where leaves from the Camellia sinensis plant are plucked at peak quality. For most teas, workers handpick only the top 2 leaves and a bud from each branch, as these tender parts of the plant produce the best flavor and aroma. After harvesting, the leaves are transported to the factory as quickly as possible to prevent spoilage or fermentation during transit. Many tea factories are strategically located near plantations to minimize delays and ensure freshness. Upon arrival at the factory, the tea leaves are weighed and inspected for quality. Modern tea factories are equipped with automated intake systems that separate leaves from debris such as twigs or foreign matter. Vibrating conveyor belts or mechanical sieves are commonly used at this stage to remove unwanted materials. For higher grade teas, additional manual inspections may be carried out to ensure only the finest leaves proceed to the next step. The fresh leaves are then carefully spread out in thin layers on large trays or conveyor belts, marking the beginning of the first stage in tea processing. Withering. Withering is a critical step in tea production, as it reduces the moisture content of the fresh tea leaves and prepares them for the subsequent stages of processing. In the factory, withering is typically carried out in withering troughs, long, shallow trays equipped with a system of fans and controlled airflow. Fresh tea leaves are laid out on these trays, and air is circulated over them for several hours to slowly remove moisture. For black tea, withering may last anywhere from 12 to 18 hours, while green tea requires a shorter withering time, as it needs to retain more of its fresh, grassy flavor. Temperature and humidity are carefully controlled using automated climate systems to ensure consistent results. During this stage, the leaves become softer and more pliable, making them ready for rolling. The next stage is rolling, where the tea leaves are twisted and shaped to release their essential oils and initiate oxidation if required, as with black and oolong teas. Factories use large mechanical rolling machines equipped with heavy, grooved plates or rollers. These machines apply pressure to the leaves, breaking down their cell walls and releasing their natural juices. The released juices react with oxygen in the air, beginning the oxidation process that gives black tea its characteristic flavor and color. Rolling machines can be adjusted to produce different shapes and textures depending on the type of tea being made. For example, green teas may be rolled into tight pellets for varieties like gunpowder tea, while black teas are often left in long, wiry shapes. At this point, the production process diverges depending on the type of tea being manufactured. For black tea, oxidation is the next key step. Oxidation, often mistakenly referred to as fermentation, is a chemical process that darkens the tea leaves and develops the rich, robust flavors associated with black tea. In factories, oxidation typically takes place in large, temperature-controlled rooms, where rolled tea leaves are spread out on trays or conveyor belts. These rooms maintain a controlled environment with high humidity and a temperature of around 77 to 86 degrees Fahrenheit. The leaves are periodically monitored to ensure they achieve the desired level of oxidation, which can take anywhere from 30 minutes to several hours, depending on the tea. As the leaves oxidize, they turn from green to a reddish-brown color, releasing the aromatic compounds that define black tea. In contrast, for green tea production, oxidation is intentionally prevented. To preserve the vibrant green color and fresh vegetal flavor of the leaves, factories employ a process called fixation, also known as kill green. This step involves heating the leaves immediately after rolling to deactivate the enzymes that cause oxidation. Factories use either steam or dry heat for this purpose. For Japanese-style green teas, like sencha, the leaves are steamed in specialized machines, while Chinese-style green teas are often pan-fried in large heated woks or rotating drum roasters. Fixation requires precise temperature control, as overheating can burn the leaves and underheating can fail to stop oxidation completely. Once oxidation or fixation is complete, the next step is drying, which reduces the moisture content of the tea to make it shelf stable. Drying is typically carried out in large industrial dryers or ovens equipped with temperature controls and airflow systems. Conveyor belt dryers, in which the leaves are gradually moved through a heated chamber, are common in large-scale tea factories. The temperature during drying ranges from 194 to 248 degrees Fahrenheit, depending on the type of tea and the desired final moisture content, which is usually around 3 to 5%. This step is crucial for locking in the flavor and aroma of the tea while ensuring it will not spoil during storage. After drying, the tea leaves are sorted and graded. In the sorting process, leaves are separated by size, shape, and quality using a combination of vibrating sieves, air separators, and optical sorting machines. Whole leaves, broken leaves, and small particles are separated into different grades, which are used for various tea products. For instance, whole leaves are often reserved for premium loose-leaf teas, while smaller particles are used for tea bags. Some factories also employ advanced laser sorting machines that can detect and remove any remaining foreign objects or off-spec leaves. Blending is another key step in tea production, especially for brands that aim to create consistent flavor profiles. Many teas are blended by mixing leaves from different regions, harvests, or even types of tea. Blending is carried out in large rotating drums or mixing machines, where precise quantities of different teas are combined to achieve the desired flavor. For flavored teas, additional ingredients such as dried fruit pieces, herbs, or essential oils are added during this stage. For example, Earl Grey tea is made by blending black tea leaves with bergamot oil, while chai blends often include spices like cinnamon, cardamom, and cloves. Once the tea has been blended and sorted, it is ready for packaging. Packaging is a highly automated process in modern tea factories. For loose leaf tea, the leaves are weighed and sealed in airtight bags, tins, or foil-lined pouches to preserve freshness. For tea bags, the leaves are measured and packed into filter paper, which is then cut and sealed into individual tea bags using high-speed machines. Many factories also produce pyramid-shaped tea bags, which allow for larger leaves and better infusion. After filling, the tea bags are placed into cartons or boxes, which are sealed and labeled with branding, lot numbers, and expiration dates. Throughout the entire process, quality control plays a vital role in ensuring the tea meets rigorous standards. Factories employ trained tea tasters who sample the tea at various stages of production to assess its flavor, aroma, and appearance. Advanced laboratory equipment is also used to measure moisture content, microbial activity, and other parameters that affect the quality and safety of the final product. Additionally, factories must comply with food safety regulations and certifications, such as ISO 22000 or HACCP, to ensure their tea is safe for consumption. Cocoa powder, the cornerstone of countless recipes from rich chocolate cakes to creamy hot cocoa, is the product of a complex and fascinating manufacturing process that combines agricultural expertise with advanced industrial engineering. Behind every tin or packet of cocoa powder lies a detailed, multi-step operation where raw cacao beans are transformed into the fine, flavorful powder that has become a staple ingredient in kitchens around the world. This process begins on cacao farms and culminates in a factory where specialized equipment and precise techniques ensure the consistency, flavor, and quality of the finished product. Let's take an in-depth journey into how cocoa powder is made, exploring each stage of the process, from bean to powder. The story of cocoa powder begins with the cacao tree, which thrives in tropical regions near the equator, such as West Africa, Southeast Asia, and Central and South America. The cacao tree produces pods that contain cacao beans surrounded by a sweet, sticky pulp. These beans are the raw material for cocoa powder. Once harvested, the pods are split open to extract the beans, which are then immediately subjected to the first critical step in the process: fermentation. Fermentation is a natural and essential process that develops the flavor precursors in cacao beans. After being removed from the pods, the beans and their surrounding pulp are placed into shallow wooden boxes or large banana leaf-lined baskets, where they ferment over a period of 5 to 7 days. During this time, natural yeasts and bacteria break down the sugars in the pulp, generating heat and causing the temperature in the fermentation pile to rise significantly, often reaching over 120 degrees Fahrenheit. This heat triggers a series of chemical reactions within the beans, developing their characteristic chocolate flavor while reducing bitterness. The beans are turned periodically to ensure even fermentation and prevent spoilage. Once fermentation is complete, the beans are removed from the boxes or baskets and sent to the next stage: drying. Drying is critical for stabilizing the fermented beans and reducing their moisture content to a level suitable for storage and transport. Traditionally, cacao beans are dried under the sun, spread out in thin layers on large drying racks or patios, and turned regularly with wooden rakes to ensure even drying. In modern cocoa production, factories may use mechanical dryers when weather conditions are unsuitable for sun drying or to speed up the process. These machines blow heated air over the beans to achieve the target moisture content, which is usually around 6 to 7%. Proper drying is essential because any excess moisture could lead to mold growth during storage or shipping. Once dried, the beans are sorted, graded, and packed into jute bags or bulk containers, ready for shipment to processing facilities. Upon arriving at the cocoa processing factory, the dried cacao beans are carefully inspected for quality. Factories use advanced optical sorting machines equipped with cameras and lasers to identify and remove defective beans, such as those that are cracked, moldy, or undersized. Any remaining debris, like stones or twigs, is removed using vibrating screens and air separators. Once the beans are cleaned, they are stored in large silos made of food-grade stainless steel, which protects them from contamination while allowing for easy access as the beans move through the production line. The first step inside the factory is roasting, a critical stage that brings out the rich chocolatey aroma and flavor of the beans. Industrial roasters are designed to handle large volumes of cacao beans, roasting them at precise temperatures that can range from 250 to 300 degrees Fahrenheit. The exact temperature and duration of roasting depend on the type of cocoa powder being produced, as darker roasts develop more intense flavors, while lighter roasts preserve subtle fruity or floral notes. During roasting, the shells of the beans become brittle, and the internal nibs, which contain the cocoa solids and cocoa butter, begin to separate from the shell. Sensors and computer-controlled systems monitor the roasting process to ensure consistency across batches. Once roasting is complete, the beans are rapidly cooled, using air or water to prevent overcooking. The next stage is winnowing, where the roasted beans are cracked open to separate the nibs from the outer shells. This process is carried out using winnowing machines, which use a combination of mechanical rollers and air currents to break the shells and blow them away. The result is a pile of clean, roasted nibs, which are the purest form of cacao and the raw material for all cocoa products. The nibs are then ground into a thick, viscous liquid known as cocoa liquor, despite containing no alcohol. The grinding process involves heavy-duty industrial grinders, such as roller mills or stone grinders, which crush the nibs into tiny particles. This process releases the natural cocoa butter within the nibs, creating a smooth liquid that flows easily. The particle size is reduced to less than 30 microns during this stage to ensure a silky texture. Cocoa liquor is the base ingredient for many chocolate products, but for cocoa powder production, the focus shifts to separating the two main components of the liquor, cocoa solids and cocoa butter. The separation of cocoa solids and cocoa butter is achieved through pressing. Cocoa liquor is fed into hydraulic or screw presses, which apply immense pressure, up to 6,000 pounds per square inch, to squeeze out the cocoa butter. This process leaves behind a solid cake of compressed cocoa solids. The extracted cocoa butter is collected and filtered for use in other products, such as chocolate bars, cosmetics, or pharmaceuticals. Meanwhile, the cocoa cake, which still contains a small amount of residual fat, becomes the foundation for cocoa powder. The cocoa cake is cooled and broken into smaller chunks before being fed into pulverizing machines, where it is ground into a fine powder. Factories use various types of grinding equipment, such as pin mills or ball mills, to achieve the desired particle size for cocoa powder. This step is critical for ensuring that the final product has a consistent texture and dissolves easily in liquids. The fineness of cocoa powder can vary depending on its intended use. For example, baking-grade cocoa powder is typically ground finer than drinking cocoa. At this point, the cocoa powder is almost ready, but one additional process may take place depending on the type of cocoa being produced. Alkalization, also known as Dutch processing. Alkalization involves treating the cocoa powder with an alkaline solution, such as potassium carbonate. This process neutralizes the natural acidity of the cocoa, darkens its color, and gives it a smoother, milder flavor. Alkalized cocoa powder is often used in baking and beverages, as its reduced acidity reacts differently with leavening agents like baking soda. Once the cocoa powder is fully processed, it undergoes rigorous quality control tests to ensure it meets the manufacturer's standards. Samples are tested for flavor, color, pH levels, fat content, and particle size. Factories use advanced laboratory equipment, such as spectrophotometers and viscometers, to measure these properties with precision. Any deviations from the desired specifications are identified and corrected before the product moves to the packaging stage. Packaging is the final step in the production process, and it plays a critical role in preserving the freshness and quality of the cocoa powder. The powder is first sifted to remove any clumps or oversized particles, ensuring a uniform texture. It is then transferred to automated filling machines, which dispense precise amounts of cocoa powder into containers, such as tins, pouches, or bulk bags. For retail packaging, the containers are often flushed with nitrogen gas before sealing to remove oxygen and prevent spoilage. Labels are applied to the packages, including information such as the brand, product type, lot number, and expiration date. Once packaged, the cocoa powder undergoes a final round of inspections, where advanced vision systems check for defects such as improper sealing, misaligned labels, or damaged containers. The finished products are then packed into cartons or cases using robotic packaging systems. Palletizing robots stack the cartons neatly onto pallets, which are shrink-wrapped for stability and loaded onto trucks or shipping containers for distribution. Manufacturing Almond Joy candy bars on an industrial scale begins long before any chocolate is melted or coconut is mixed. It starts with the careful sourcing and preparation of one of the candy's most iconic and defining components, the coconut. This isn't just any shredded coconut. This is a specific, moisture-balanced, finely textured variety that gives Almond Joy its distinct chewy center. Producing coconut to these specifications requires a highly controlled and deliberate process. And in modern facilities, this step alone involves extensive coordination between agricultural suppliers, food scientists, and processing engineers. The coconuts used in Almond Joy bars are primarily sourced from tropical regions like the Philippines, Indonesia, and India, where coconut palms grow in warm, humid climates and are harvested multiple times per year. The coconuts are selected based on strict criteria such as maturity, size, and oil content, all of which contribute to the flavor and structure of the final product. After harvesting, the outer husks are mechanically removed using rotary dehusking machines, exposing the inner brown shells. These shells are then cracked open using high-torque hydraulic presses or mechanical splitters, allowing access to the white coconut meat inside, also known as copra. Once separated from the shell, the coconut meat is washed in large stainless steel tanks using filtered water, sometimes with a light chlorine solution to remove any contaminants, shell fragments, or residual dirt. The clean coconut meat is then graded using high-speed rotary shredders, which reduce it into uniform strands. These industrial shredders operate at several thousand RPMs and are fitted with specialized blades designed to achieve a consistent flake size. The exact dimensions of the shredded coconut are critical. Too coarse, and the texture becomes stringy. Too fine, and it loses its chewiness. The shredded product is then passed through vibratory sieves to remove any oversized or undersized particles, ensuring each flake meets factory specifications. Once the coconut is shredded and sized, it undergoes a drying phase designed not to fully desiccate the coconut, but to bring its moisture content into a very specific range, typically between 12 and 14%. This drying process is carried out in large belt dryers or fluidized bed dryers that blow heated air over the coconut shreds while keeping them suspended and moving, ensuring even drying throughout. Sensors embedded in the dryer constantly monitor moisture levels in real time, allowing for micro adjustments to airflow and temperature. This precision ensures that the final coconut retains its soft, moist chewiness without being wet or prone to microbial spoilage. Once dried, the coconut is cooled with ambient air and sent through a metal detection system before being packed into sterile bulk totes or drums, ready to be delivered to the candy production line. Now it's time to go into the coconut syrup blending process, where the prepped coconut is transformed into the moist, sweet filling that forms the base of every Almond Joy bar. At this stage, the dried coconut shreds are transferred from storage bins into large stainless steel ribbon blenders or planetary mixers. These mixers are food grade and designed to gently fold the ingredients together without compressing or overworking them, which would damage the texture. While the coconut is being added to the mixer, a separate part of the factory is simultaneously preparing a sugar syrup that will serve as the binder and sweetener. This sugar syrup is cooked in large steam-jacketed kettles, each fitted with agitators and temperature sensors. The syrup typically contains a blend of sucrose, corn syrup, and a small percentage of invert sugar, which helps prevent crystallization and keeps the final mixture smooth and cohesive. The ingredients are combined with water and brought to a boil, then held at a precise temperature of around 230 to 240 degrees Fahrenheit. Once the syrup reaches the desired consistency and viscosity, it is pumped through insulated transfer lines into the mixers containing the shredded coconut. The hot syrup is slowly added into the mixing chamber while the paddles rotate at a controlled speed, ensuring that every strand of coconut becomes evenly coated. This mixing step is closely monitored for torque resistance, an indirect measure of viscosity and saturation. If the mixture becomes too stiff, it indicates that not enough syrup has been added, while an overly slack consistency could suggest too much moisture. Adjustments are made in real time, either by slowing down the mixing blades or by adding additional syrup in carefully measured quantities. The end result is a glossy, dense, and aromatic coconut mixture with a smooth mouthfeel and a controlled stickiness that allows it to hold together when molded. This freshly prepared filling is discharged from the mixer into temperature-controlled holding hoppers. From there, it is fed through sanitary auger systems into the forming line, where the next phase of production begins, shaping each bar's core. But up next is the forming process, where this cohesive coconut mixture is portioned and molded into the rectangular log shape that defines the inner core of every Almond Joy. This step is handled by a specialized extrusion and forming system. The mixture is continuously extruded through a die system that determines the width and height of the log. These forming dies are custom designed for Almond Joy and produce a consistent cross-section with slightly rounded tops, ensuring a uniform bite and a reliable surface for almond placement. The extrusion head releases a continuous ribbon of coconut mixture onto a moving conveyor belt, and a high-speed rotary guillotine, timed with the conveyor's speed, cuts this ribbon into individual bar-length pieces. The distance between each cut is controlled down to the millimeter, and a sensor-based feedback system ensures that every bar is exactly the same size. After cutting, a short air blast is applied to each log to clear away any stray coconut flakes and ensure clean edges. As the bars are cut, they enter a cooling conveyor that travels through a tunnel kept at approximately 45 degrees Fahrenheit. The cooling process is essential at this point. Not only does it help the bars hold their shape, but it also stabilizes the sugar syrup binder so that the mixture doesn't slump or deform in the next step. A key consideration during this cooling stage is air humidity. If the environment is too dry, the coconut can begin to crust or dry out. Too humid, and condensation may form, which can affect downstream adhesion with the chocolate coating. For this reason, industrial humidity control units maintain relative humidity levels around 45 to 55% inside the cooling tunnel. Once cooled and firmed, the coconut logs are transferred by conveyor to the almond placement system. Each log must receive exactly 2 whole almonds, neither more nor less, positioned evenly across the top surface. The almonds used in this process are themselves the result of a careful preparation sequence. Raw almonds are sourced from large-scale growers, often in California, and are received at the factory in bulk containers. These almonds are sorted, cleaned, and then dry roasted in large convection ovens. Roasting enhances flavor, reduces moisture to less than 5%, and gives the almonds the crunch consumers expect. After roasting, the almonds are cooled and transported to a hopper above the placement system. Here, they are singulated, separated into single file, and guided into individual almond placement arms. These arms are controlled by a vision-guided robotic system that tracks the position of every coconut log in real time. Using photoelectric sensors and high-resolution cameras, the system places each almond with millimeter-level accuracy on top of the log. The almonds are pressed into the surface just enough to adhere without sinking, and an inline inspection system checks that every bar has precisely 2 almonds aligned correctly. Any bar that deviates from this standard is removed from the line for manual inspection or rework. Now it's time to go into the chocolate enrobing stage, which marks the beginning of the transformation from a basic assembly of ingredients into the finished, glossy, consumer-ready candy bar. This process involves fully coating the almond-topped coconut cores with a layer of milk chocolate. But this is no ordinary chocolate. It has been specifically formulated and tempered to provide the right snap, shine, and melt-in-the-mouth texture that defines the almond joy eating experience. The chocolate is stored in holding tanks maintained at 110 to 115 degrees Fahrenheit and stirred continuously to ensure it remains fluid and free from separation. Before use, the chocolate is tempered through a process that heats, cools, and reheats it to align the cocoa butter crystals in a stable form. Proper tempering is essential as it prevents fat bloom and gives the coating its glossy finish and clean break. The tempered chocolate is pumped into an enrobing machine, which dispenses it in a continuous curtain across the width of the conveyor belt. As the coconut and almond cores pass underneath, they are fully submerged in the falling sheet of chocolate, while a bottoming unit applies a layer of chocolate to their underside. Immediately afterward, a series of air blowers remove excess chocolate, ensuring a uniform thickness and revealing the shape of the almonds beneath. What emerges is a fully coated bar that looks and feels like the final product, but still needs time to set. That step begins as the bars enter a temperature-controlled cooling tunnel, and that's where the next phase begins. Inside the cooling tunnel, a meticulously engineered, climate-controlled chamber extending over 30 feet in length, the freshly enrobed Almond Joy bars begin their chocolate setting phase. This tunnel is one of the most crucial parts of the process, ensuring that the tempered chocolate coating transitions from a glossy liquid into a solid shell with the perfect texture and finish. The chocolate must cool at a precise rate, not too fast, which could result in cracking or sugar bloom, and not too slowly, which could cause the cocoa butter crystals to misalign, leading to dullness or fat bloom on the surface. The tunnel operates at an ambient temperature between 45 and 55 degrees Fahrenheit, and relative humidity is tightly controlled around 50%. High-efficiency fans circulate cold air evenly across all bars on the conveyor, and temperature sensors track minute variations along the length of the tunnel. The speed of the conveyor is carefully synchronized with the chocolate's crystallization curve so that the bars spend just the right amount of time cooling, usually between 7 and 12 minutes, depending on environmental conditions, line speed, and chocolate thickness. During this stage, the chocolate coating fully hardens around the coconut and almond core, creating a glossy, smooth outer layer that locks in moisture and flavor. The almonds, having been gently pressed into the top of the coconut before enrobing, remain clearly visible through the chocolate shell, creating the bar's iconic bumpy silhouette. As the bars exit the tunnel, they are now fully formed, with all primary ingredients integrated and stabilized. But the next phase, inspection and quality control, ensures that only perfect bars make it into the hands of consumers. The next step is the multi-layered inspection and quality assurance phase, a critical junction in the Almond Joy manufacturing process. Here, each fully cooled, enrobed bar passes under a series of digital scanning systems equipped with high-resolution cameras and sensors that detect inconsistencies in shape, size, and appearance. These systems analyze every bar in real time using image recognition algorithms trained to identify surface defects, incomplete chocolate coverage, missing almonds, or any signs of misalignment. Each camera system captures dozens of images per second, creating a detailed digital fingerprint of each bar. If a defect is detected, such as an air bubble on the surface, a chocolate smear, or a misaligned almond, the bar is automatically rejected using a quick puff of compressed air that directs it off the main conveyor into a designated collection tray. Rejected bars are recorded and analyzed in quality control logs to monitor trends and flag any upstream issues in real time, like syrup inconsistencies or almond placement variances. Following the visual inspection, the bars pass through an inline check weighing station. This precision balance system measures the mass of each individual bar down to the 1/10 of a gram. Bars that are even slightly under or overweight are flagged and rejected from the line. This strict weight control not only ensures product consistency and consumer satisfaction, but also regulatory compliance, as all packaged goods must meet labeled net weight declarations. These check weighers are recalibrated frequently during production to maintain absolute accuracy, and the results are logged digitally to provide traceable batch records. Next, a random sampling process is initiated where trained human inspectors pull sample bars from the line every few minutes. These samples are taken to a nearby quality assurance room for deeper evaluation. Inspectors slice open the bars and examine the cross-section for proper ingredient distribution, moisture retention in the coconut layer, almond placement, and shell integrity. Taste testing is performed by a trained sensory panel in a separate tasting room to ensure the flavor profile remains consistent. Parameters like sweetness, chewiness, and chocolate snap are all evaluated and recorded in a detailed quality report. Once bars have successfully passed through the inspection phase, they are ready for the next stage, packaging. But up next is the flow wrapping process, where each Almond Joy bar is individually wrapped using high-speed machinery designed to maintain hygiene, preserve freshness, and uphold branding consistency. The packaging film, pre-printed with the Almond Joy logo and product information, is loaded in giant rolls at the start of the packaging line. These rolls are threaded through a series of rollers and tensioners that keep the film aligned and taut as it's fed into the wrapping unit. The bars are spaced and synchronized onto a conveyor lane and fed into the flow wrapping machine, which envelopes each one in film and seals it at the sides and ends using heated crimping jaws. These jaws press the film together and apply controlled heat and pressure to create airtight seals that are strong yet easy to open. The sealing temperatures are carefully monitored to avoid overheating the chocolate within, as excess heat could cause the surface to dull or soften. Each wrapped bar is then passed under a thermal inkjet or laser coder, which prints the best before date, batch code, and production time directly onto the wrapper. This traceability information is vital in case of recalls, inventory tracking, or shelf life analysis. Vision sensors verify the presence and clarity of the code, and any missing or illegible codes trigger a rejection mechanism. The speed of this entire process is remarkable. Modern flow wrappers can handle upwards of 500 bars per minute, all synchronized perfectly to match the upstream enrobing output. Once wrapped and coded, the Almond Joy bars are grouped into retail-ready formats. Depending on the destination, this could mean twin packs, king-size versions, or standard singles in cartons. Cartoning machines fold and glue cardboard sleeves or cartons, then insert the correct number of bars automatically. These cartons are scanned for correct orientation, closed, and labeled with shipping and SKU data. A final check weigher ensures that the total weight of each carton falls within specification, and the completed units are then moved down the line to case packing. The case packing phase involves automated robotic arms or pick-and-place systems that lift finished cartons and place them into larger, corrugated shipping cases. The arrangement within each case is optimized for pallet stability and protection during transit. Each case is labeled with product identifiers, batch codes, and destination information, then sealed and conveyed to a palletizing station. Palletizing robots stack the cases onto wooden or plastic pallets in precise configurations to maximize space and maintain structural integrity during transport. Once a full pallet is assembled, it's wrapped in high tensile stretch film using automated rotary arm or turntable wrappers. This wrapping secures the load against shifting during transportation and also provides a barrier against dust and moisture. Each pallet is then tagged with a barcoded shipping label that includes tracking information, weight, and customer-specific handling instructions. The completed pallets are moved to a climate-controlled storage area within the warehouse to await shipment. Now, it's time to go into the logistics and distribution stage, where the focus shifts from production to coordinated movement and inventory management. Almond Joy bars, like all Hershey's products, are managed within an enterprise resource planning system that tracks production batches, inventory turnover, and customer orders in real time. Based on demand forecasts, pallets are selected for outbound shipment, assigned to specific trucks or containers, and scanned out of the warehouse with full digital traceability. Transport is typically handled using refrigerated trucks during warmer months, as the milk chocolate in Almond Joy bars is sensitive to heat. Temperatures are maintained between 55 and 65 degrees Fahrenheit during transit, and GPS-linked thermal loggers monitor each vehicle's internal climate from origin to delivery. If a truck deviates from its safe range, alerts are sent to both logistics managers and warehouse supervisors to prevent spoilage. Once the bars reach regional distribution centers or retail warehouses, the product is scanned into inventory and routed to store shelves. Retail partners rely on synchronized inventory systems that replenish stock as it sells, often based on point-of-sale data. The entire journey, from Coconut Grove to grocery store, can be completed in just a matter of weeks, but every phase must function flawlessly to deliver a bar that meets Hershey's standards for quality, freshness, and consistency. And even once the product hits shelves, the factory's job isn't done. Ongoing consumer feedback, seasonal demand changes, and promotional cycles influence continuous adjustments in batch sizes, production schedules, and packaging variations. Special holiday versions, multi-packs, and limited time offers are all planned months in advance and require tailored processes, new molds, and reprogrammed machinery, an impressive level of flexibility embedded within an otherwise standardized production system. Quality assurance continues to play an active, ongoing role in the manufacturing of Almond Joy, even after the bars have been wrapped, packed, and prepared for distribution. In fact, behind the scenes of the main production line, a parallel infrastructure operates continuously to monitor, record, and validate every element of the process in real time and long after the initial production phase. This includes not only in-process checks, but detailed post-production sampling and retention, which are central to traceability, regulatory compliance, and product consistency. One critical ongoing practice is the archiving of batch samples. As bars are wrapped and prepared for shipment, dedicated staff routinely pull random samples from each batch, often one every few thousand bars. These samples are sealed, labeled, and logged with all relevant metadata: the exact time of production, line number, raw material codes, chocolate viscosity at time of enrobing, coconut moisture content, and even almond roast profiles. These reference bars are stored in secure, climate-controlled storage units maintained at conditions that mimic ideal shelf environments. The goal is to preserve these products in a stable state for up to 2 years, during which time they may be retrieved for comparison if any quality concerns or deviations arise. In addition to acting as an insurance policy against customer complaints or distributor queries, these archived samples are regularly tested as part of long-term shelf life studies. Trained quality assurance technicians perform controlled aging studies by artificially accelerating the aging process in heated chambers to evaluate how the product will hold up over time. These studies track changes in coconut chewiness, chocolate bloom resistance, almond crunch retention, and overall flavor integrity. Sensory analysis is conducted by expert panels who evaluate sweetness, aroma, textural contrast, and mouthfeel using standardized scoring systems. This data feeds back into ingredient sourcing decisions and packaging refinements, allowing the team to adjust variables well before any potential issues could reach consumers. Now, it's time to go into the digital control systems that operate silently beneath every piece of equipment, coordinating, recording, and adjusting every stage of the Almond Joy production process. At the core of this system is a network of programmable logic controllers, PLCs, which manage the real-time operation of machinery across the factory floor. These industrial computers are programmed to respond to sensor inputs and control outputs with extreme precision, enabling the synchronization of critical events such as syrup dosing, coconut extrusion, chocolate tempering, and wrapper sealing. For example, if the syrup temperature in the blending kettle falls even slightly below the optimal range of 235 to 240 degrees Fahrenheit, the PLC will automatically trigger a compensatory adjustment in steam pressure. Similarly, if a sensor detects that the chocolate curtain in the enrober has begun to thin, indicating an issue with flow rate or chocolate viscosity, the system can alter pump speed, activate an agitator, or send an alert to the line technician. These reactions happen in milliseconds, ensuring seamless operation with minimal human intervention. All this data funnels into a supervisory control and data acquisition system, or SCADA, which acts as the digital nervous system of the plant. SCADA systems provide centralized visualization of every variable in production, from torque readings in the coconut mixes to conveyor belt speeds on the packaging line. Live dashboards display real-time metrics alongside historical trends, and operators can set control limits to trigger alarms, shutoffs, or automatic corrective actions when deviations occur. Data logging is continuous, with every action time-stamped and stored in redundant backups for audit and analytics purposes. But up next is the role of continuous improvement teams and how they use this wealth of production data to fine-tune the manufacturing process. Rather than viewing each shift as a discrete operation, modern Almond Joy factories treat every minute of production as a learning opportunity. Statistical process control specialists and lean manufacturing engineers analyze massive volumes of data to identify small but significant trends. For instance, if there's a subtle uptick in the rate of chocolate flow variation on line 2 during evening shifts, it might suggest thermal drift in the tempering unit, or minor calibration errors in the chocolate pump. These insights allow preventive maintenance schedules to be updated, saving time and resources while minimizing the risk of future disruptions. Some adjustments are made on the spot, while others lead to full pilot testing cycles. Pilot lines, scaled-down versions of the full production setup, allow engineers to test adjustments to temperature profiles, mixing durations, or conveyor speeds without interrupting primary operations. For example, if a new batch of coconut arrives with slightly higher fat content than normal, the pilot team may experiment with modified syrup ratios or mixing times to maintain the same moisture binding characteristics. Results are measured using laboratory tools like refractometers, rheometers, and moisture analyzers. And the most successful configuration is then rolled out to full production. The focus on fine-tuning doesn't stop at equipment and ingredients. It also extends to the behavior of the product throughout the supply chain. Some Almond Joy bars are shipped across the country or even internationally, and that means packaging and formulation must perform under a wide range of conditions. Engineers perform transit simulations using vibration tables and thermal chambers to replicate the effects of long-distance trucking or air freight. These simulations allow packaging specialists to evaluate wrapper integrity, seal strength, and chocolate stability under heat and motion stress. In cases where performance can be improved, new materials or layering structures are proposed, often months before the consumer ever sees the final package. The industrial production of condensed milk begins with the careful reception and preparation of raw cow's milk, a phase that determines the quality, efficiency, and final yield of the entire operation. As raw milk arrives at the condensed milk manufacturing facility, typically transported in insulated stainless steel tankers from contracted dairy farms, the first priority is immediate and rigorous quality assessment. Each truckload contains tens of thousands of liters of milk, and every batch must be verified to meet precise industrial standards before being accepted into the plant's supply chain. This initial phase involves a set of standardized protocols carried out in a dedicated receiving bay, equipped with specialized sampling and testing equipment. Upon arrival, the truck is docked to an unloading station, where automated lines connect directly to the tanker's valve. Before unloading can commence, operators perform a series of tests on a representative sample extracted from the tanker. This is done using a sanitized dipper or through a sample port using aseptic techniques to avoid contamination. The sample is then transferred to the plant's on-site quality control lab. Inside this lab, technicians first conduct a sensory inspection, evaluating the milk's color, smell, and presence of any visible particulates. While this step is basic, it's essential in immediately identifying any batches with gross spoilage or foreign contamination. The next series of tests are chemical and microbiological. A cryoscope is used to determine the freezing point of the milk, which helps identify dilution with water. Industrial condensed milk relies on unadulterated raw milk with tightly controlled fat and solids not fat contents. Any dilution affects the solids concentration required for the evaporation phase later on. Following this, infrared spectroscopy or mid-infrared analyzers are used to determine precise fat, protein, and lactose levels. These readings are compared against production targets, usually 3.5 to 4.0% fat and 8.5 to 9.0% SNF. If any component falls out of range, the milk may be either rejected or diverted to other dairy product lines. Another critical check is for microbial load. A rapid plate count, or ATP bioluminescence test, evaluates the total bacterial count per milliliter. Condensed milk production cannot start with high bacterial loads, as the concentration process would also concentrate any microbial byproducts, leading to off flavors and safety risks. Acceptable raw milk generally must have fewer than 100,000 colony-forming units per ml, with many plants enforcing even tighter limits. Additionally, presence of pathogens such as Listeria or Salmonella are monitored using immunoassay kits or PCR-based rapid tests. Antibiotic residue testing is also performed using either SNAP tests or microbial inhibition assays, since antibiotic contamination can disrupt the fermentation steps used in other dairy operations and might violate export regulations. If the sample passes all tests, the milk is cleared for unloading. The truck's contents are then pumped via sanitary stainless steel pipelines into raw milk holding tanks located within a temperature-controlled section of the facility. These tanks, typically ranging from 20,000 to 50,000 litres in capacity, are jacketed and agitated to maintain a constant temperature of around 4 degrees Celsius. At this stage, the milk is still unpasteurized and considered perishable, so time and temperature control are critical. The tanks are equipped with inline thermometers and CIP spray balls that will sanitize the internal surfaces between batches to prevent cross-contamination. The next step in the process is milk clarification and standardization. This is a pivotal moment where physical impurities and excess variability in composition are removed. The raw milk is fed from the storage tanks to a centrifugal clarifier, a high-speed rotating bowl separator that uses the density differences between milk solids and liquid to remove somatic cells, dirt, and other non-milk particles. The milk enters the spinning drum through a feed pipe, and under centrifugal force, heavier particles are flung outward against the bowl walls and discharged intermittently via sludge ejection ports. After clarification, the milk is sent to a cream separator. This piece of equipment operates similarly to the clarifier, but focuses on removing and isolating the cream layer from the skim milk portion. Depending on the desired end product specifications, some or all of the separated cream may be blended back in. This is where the standardization process comes into play. Condensed milk requires a tightly defined balance between fat content and total milk solids. Operators adjust this balance using inline blending systems, automated control loops equipped with flow meters and density sensors. The goal is to create a uniform milk base, typically around 8.5% fat and 22% total solids, before it proceeds to pasteurization and evaporation. Any deviation at this stage would affect the efficiency of the next stages and could compromise the desired thickness, sweetness, and shelf life of the condensed milk. In more advanced factories, these composition adjustments are performed entirely by automated PLC systems. These use real-time data collected from inline sensors to control proportioning valves and regulate the mixing of cream and skim milk streams without any manual input. This level of automation not only ensures consistency, but reduces waste and energy use. The standardized milk is now homogeneous in composition, free of debris, and ready for thermal treatment. Before entering the pasteurizer, it may pass through a deaerator, a vacuum chamber that removes entrapped gases such as oxygen and carbon dioxide, which, if left in, could promote oxidation of fats and off flavors during storage. But up next is a step that changes the physical properties of the milk at a fundamental level. With the raw milk now cleaned, standardized, and compositionally balanced, it's time for it to undergo pasteurization and heat treatment, a step that prepares it for concentration without microbial risk or protein denaturation. This phase involves an intricate dance between temperature, pressure, and time, and it sets the stage for the transformative evaporation process that gives condensed milk its name. Now that the raw milk has been thoroughly received, clarified, and compositionally standardized, it is ready for thermal treatment. The next phase in the factory process is pasteurization, which is critical in destroying any pathogenic or spoilage microorganisms present in the milk. pasteurization must be done with precise timing and temperature control to ensure microbial inactivation without damaging the milk's nutritional or functional properties, especially since this milk will soon undergo evaporation, which puts it under further thermal stress. To carry this out, the milk is directed from the holding tanks into a continuous flow, high-temperature, short-time pasteurization unit, which is the standard in industrial dairy processing. The HTST system typically consists of a series of plate heat exchangers that are engineered to raise the milk temperature to approximately 85 degrees Celsius for 15 to 20 seconds. This is hotter and slightly longer than conventional drinking milk pasteurization, as condensed milk requires greater microbial stability due to its extended shelf life. The process begins in the regeneration section of the plate heat exchanger, where incoming cold raw milk is preheated by outgoing pasteurized milk, allowing energy recovery and efficiency gains of up to 90%. The milk then moves through the heating section, where it is brought to the target temperature using hot water or steam circulated on the opposite side of the stainless steel plates. The timing of exposure is controlled by the flow rate and volume of the holding tubes, ensuring that every particle of milk receives uniform treatment. After pasteurization, the milk passes into a holding cell monitored by thermocouples and flow diversion valves. If the milk fails to reach or maintain the required pasteurization conditions, it is automatically diverted back to the raw milk tank for reprocessing. Once verified, the pasteurized milk is cooled again in the regeneration section, where it gives off its heat to the incoming raw milk, and then further chilled to around 60 degrees Celsius in preparation for the next crucial step, evaporation. Before entering the evaporator, the milk passes through a balance tank that helps maintain a constant feed rate into the evaporation system, stabilizing flow and avoiding temperature fluctuations that could cause burn-on or fouling inside the evaporator tubes. Now it's time to go into the evaporation stage, which is arguably the heart of the condensed milk production process. This is where the milk is physically transformed, thickened into a rich, viscous product through the removal of water. The goal here is to reduce the water content from its original 87% down to around 60%, achieving a final concentration of about 28% milk solids and 44% added sugar in the case of sweetened condensed milk. This is achieved through multi-effect vacuum evaporation, an energy-efficient process that allows for large-scale water removal without subjecting the milk to damaging high temperatures. The milk enters a multiple effect falling film evaporator, which is the industry standard for large volume dairy processing. In this system, the pasteurized milk is introduced at the top of vertical stainless steel tubes, where it forms a thin film as it flows downward. Simultaneously, steam is injected into adjacent chambers that surround the tubes, heating them indirectly. Because the evaporator is operated under vacuum, often at pressures around 70 to 100 millibar, the boiling point of the milk is reduced to around 55 degrees Celsius. This protects the sensitive proteins, sugars, and fats from heat-induced damage, preserving both flavor and nutritional quality. In a multi-effect setup, the vapor produced from one stage is used to heat the next stage, drastically improving energy efficiency. A typical 5-effect evaporator can remove over 85% of the water from milk with minimal energy input, thanks to this cascading reuse of thermal energy. The evaporated water is condensed and collected as waste heat condensate, which can later be recycled within the plant for cleaning processes or steam generation. Inside the evaporator, the thin film of milk continuously loses moisture as it falls. The combination of short residence time, low boiling point, and efficient heat transfer ensures that concentration occurs evenly and rapidly. By the time the milk reaches the bottom of the final effect, it has reached a viscous, concentrated state with a solid content of around 45%. At this point, it is discharged into an intermediate concentrate tank, where it is gently agitated and kept warm to prevent crystallization or skin formation on the surface. But the evaporation process alone does not fully define condensed milk as we know it, especially in the case of sweetened condensed milk. Once the desired solids concentration is achieved, the next critical step is the addition of sugar, which is not merely for taste, but serves as a functional preservative. The high sugar content lowers the water activity of the product to a point where microbial growth is virtually halted, granting it a long shelf life without refrigeration. The method of sugar addition must be extremely precise, as the wrong concentration can lead to issues like crystallization, viscosity problems, or even fermentation in rare cases. To do this, refined white sugar, typically sucrose, is added to the concentrated milk in the form of a hot sugar syrup. This syrup is prepared separately in jacketed mixing vessels, where dry granulated sugar is dissolved in water and heated to around 70 degrees Celsius. The syrup is filtered to remove any particulate matter and pumped into the concentrate tank under controlled flow rates. The typical formulation is around 46% sucrose by weight in the final product, which is determined by a combination of inline refractometers and density meters. The mixing of sugar syrup into the concentrate must be uniform to prevent localized crystallization and is often aided by low shear agitators that maintain homogeneity without introducing air. As the sugar is added, the milk becomes even more viscous and dense. At this point, the product's temperature is carefully maintained between 60 degrees Celsius and 65 degrees Celsius, as dropping below this range can initiate premature crystallization, while higher temperatures can scorch the milk solids. Once the sugar is fully integrated, the mixture is briefly held in a jacketed holding tank for a process known as equilibration, which allows any remaining air bubbles to rise and dissipate and gives time for the solution to reach equilibrium in terms of water activity and solute concentration. This marks the end of the thermal and compositional transformation stages. From a microbiological and physicochemical standpoint, the product is now shelf-stable, viscous, and chemically preserved by both heat treatment and high sugar concentration. However, it's not yet ready for packaging. There are still important steps to take involving cooling, crystallization control, and downstream finishing that are vital to achieving the smooth texture and glossy appearance that define high-quality condensed milk. With the concentrated sweetened milk now fully blended and equilibrated, the next critical phase in the condensed milk manufacturing process is controlled cooling and crystallization. This step is vital not only to achieving the desired texture and viscosity, but also to ensuring long-term product stability. If cooling is done too quickly or without proper control over nucleation, the lactose and sucrose in the product can crystallize into large, gritty particles. This not only affects mouthfeel, but can also lead to phase separation over time. To avoid this, the condensed milk is sent through a carefully engineered cooling and seeding system that promotes the formation of microcrystals, small, evenly distributed sugar crystals that give condensed milk its signature smooth, glossy consistency. The cooling system typically consists of scraped surface heat exchangers or jacketed tubular coolers. These systems are designed to handle highly viscous liquids and provide a high degree of thermal control. In scraped surface heat exchangers, the condensed milk flows through a cylindrical barrel while rotating blades constantly scrape the inner surface. This ensures that no product burns or sticks to the hot surface, and that the entire volume of milk is uniformly cooled. The cooling medium, usually chilled glycol or water, is circulated through the jacket, gradually lowering the milk temperature from around 65 degrees Celsius to 30-35 degrees Celsius. As the milk cools, it passes through a crystallization chamber where it is inoculated with fine lactose or sucrose seed crystals. These seed crystals are introduced in a controlled manner using a dosing system that meters out microscopic crystals with a high surface area. The goal is to initiate crystallization at a molecular level, encouraging the dissolved sugars to form consistent and extremely fine crystals rather than large, coarse ones. Agitators in the crystallization chamber are designed to promote gentle but thorough mixing, ensuring uniform distribution of the seed material without incorporating excess air, which could lead to oxidation or microbial contamination. Once seeded, the mixture is held at a stable crystallization temperature, typically around 30 degrees Celsius, for a period ranging from 30 to 90 minutes, depending on the batch size and product formulation. This resting period allows the crystals to grow slightly while remaining small and suspended, forming a delicate lattice within the viscous matrix of the milk. It is during this stage that the final texture of the condensed milk is locked in. Operators closely monitor the product's Brix value, viscosity, and temperature, using inline sensors and laboratory sampling to ensure that the crystallization proceeds according to specification. After the crystallization phase, the product enters the deaeration stage. Despite all precautions taken during processing, the condensed milk will inevitably contain some entrapped air, either from mechanical mixing, seeding, or agitation. This air must be removed before packaging to prevent oxidation, which can degrade both flavor and color over time. Deaeration also helps improve fill accuracy during packaging, ensuring a stable and uniform product weight in each container. Deaeration is typically carried out in a vacuum deaerator tank. The condensed milk is pumped into the tank, which is maintained under a vacuum of around -0.8 bars. Inside the tank, the milk is spread into a thin film across a series of rotating trays or falling film surfaces, maximizing the exposed surface area. As the product spreads out under vacuum, dissolved gases and trapped air are released and drawn out by the vacuum pump system. In some systems, nitrogen gas is also bubbled through the product as a stripping agent to help displace oxygen more effectively. This process is continuously monitored with oxygen sensors to ensure minimal residual oxygen levels in the final product, typically less than 0.5 milligrams per liter. Once deaerated, the condensed milk is often passed through a final homogenization stage. While not strictly required in all formulations, homogenization is frequently used to improve product consistency, prevent fat separation, and extend shelf stability. In this process, the milk is forced through a narrow orifice under high pressure, usually between 100 to 150 bar, causing the fat globules to break down into much smaller sizes, typically less than 1 micron in diameter. This prevents creaming or separation during storage and gives the final product a more uniform mouthfeel. The homogenizer used in this step is typically a 2-stage piston-type homogenizer. In the first stage, pressure is applied to break apart the fat globules. In the second stage, the product is passed through an impact ring to further disperse and stabilize the emulsion. This ensures that the fat remains evenly distributed throughout the viscous condensed milk matrix, even after months of storage on a shelf. The process must be carefully balanced to avoid over-shearing the product, which could break the sugar crystal structure and lead to syneresis or texture issues. With the product now fully processed, it moves to the packaging line. Before any milk enters a can or a tube, the packaging material itself must undergo preparation. Metal cans are the most common format for condensed milk, though plastic tubes and laminated pouches are also used depending on market demands. The cans arrive at the factory either as pre-formed containers or as rolled flat blanks that are formed and sealed on site using can-forming machinery. If using pre-formed cans, the first step is depalletizing and feeding. The cans are automatically unloaded from shipping pallets and fed into a cleaning system via conveyor belts. Here, they pass through a high-pressure air blower system that removes dust and debris. They may also pass through an inverted rinse tunnel that sprays them with sterile water or a mild sanitizing solution. Optical sensors verify that each can is intact and free of damage before it proceeds. The clean cans are then transported to the filling station, where they are indexed into position beneath nozzles connected to a positive displacement filler system. These filling machines are designed to handle thick, viscous liquids with high precision. A typical condensed milk filling machine includes a volumetric dosing mechanism that ensures every can receives the exact same quantity, usually around 397 grams, the standard retail size. Sensors ensure the nozzles do not drip or splash, and the filling process is conducted in a low oxygen environment to prevent post-process contamination. As cans are filled, they immediately move to the vacuum closing station. This is another critical step in ensuring product longevity. Before the lid is sealed, a vacuum is applied to the headspace in the can to remove residual air. This helps prevent oxidation and maintains the slight negative pressure required for a tight seal. The lid is then applied and hermetically sealed using a double seaming machine. This creates an airtight seal by mechanically folding and compressing the lid and can flange together in 2 operations. The quality of this seal is checked automatically using seam gauges and vision inspection systems to detect any defects or incomplete closures. After sealing, the cans enter a hot water bath or steam chamber for thermal holding. This step, known as in-can sterilization or thermal stabilization, involves heating the sealed cans to around 85 to 90 degrees Celsius for 15 to 20 minutes. This serves several functions. It neutralizes any residual microbes that may have entered during filling, helps equalize pressure inside the can, and further reduces the water activity of the product. The heating process is tightly controlled using a time temperature data logger to ensure consistency across batches. Once the thermal holding is complete, the cans are rapidly cooled using chilled water sprays or immersion tunnels. This quick cooling halts the cooking process and helps set the product structure inside the can. It also prevents over-darkening, which can occur due to Maillard reactions between milk proteins and sugars at elevated temperatures. The cans are then dried using air knives and conveyed to the labeling and coding area. Each can is now labeled with full product information, including nutritional facts, production batch codes, expiration dates, and allergen warnings. Laser coders or inkjet printers apply traceability codes directly onto the lid or bottom of each can, allowing for full tracking throughout the supply chain. These codes are critical for food safety as they allow for rapid recall or identification of affected batches in the rare event of a contamination issue. From here, the cans are packed into cartons or shrink-wrapped into bundles using automated case packers. The cartons are stacked onto pallets and wrapped with stretch film for transport. At this stage, finished condensed milk is subjected to final quality inspection, where random samples from each batch are tested for Brix value, fat content, microbial load, viscosity, and packaging integrity. Once the batch is cleared, it is released for distribution. With the cans now fully sealed, labeled, and palletized, the condensed milk moves into the final stretch of its industrial journey: post-production storage, distribution, and market readiness. While it may seem that the heavy lifting is over, these concluding steps are far more complex and technologically managed than they first appear. Factories invest significant resources to ensure that every can of condensed milk not only leaves the facility in perfect condition, but also maintains its quality throughout the entire shelf life, often up to 2 years or more. Immediately after packaging, pallets of condensed milk are transferred to temperature-controlled finished goods warehouses. The climate in these storage areas is tightly regulated, typically kept between 15 degrees Celsius and 25 degrees Celsius, with relative humidity under 60%. This environment prevents moisture accumulation on the can surfaces and limits the rate of any chemical reactions inside the product, such as non-enzymatic browning. Even though the condensed milk is shelf-stable, excessive heat over time can darken the color and subtly change the flavor profile. These storage conditions are monitored 24/7 using IoT-connected environmental sensors that send real-time data to the facility's central control system. Each pallet is barcoded with batch numbers and entered into a digital warehouse management system. This system not only tracks location and inventory levels, but also enforces FIFO protocols to ensure older batches are distributed before newer ones. The traceability codes printed earlier on the cans come into play again here. Every single unit can be traced back to its raw milk intake, processing parameters, operator ID, and time-stamped process logs. This full chain traceability is a critical part of modern food safety compliance. When orders are received from retailers, exporters, or institutional buyers, automated robotic pallet pickers retrieve the relevant stock and move it to the outbound shipping area. Here, it is loaded into refrigerated or insulated trucks, depending on the destination and regional climatic conditions. In many cases, international shipments involve placing pallets into reefer containers that maintain stable temperatures for transoceanic shipping routes. It all begins with the careful sourcing and intake of raw chicken, a process that is both biologically sensitive and highly mechanized to maintain consistent quality and food safety. The chickens destined for KFC facilities are selected from specific poultry farms that follow stringent guidelines set by both KFC's corporate standards and local regulatory bodies. These farms raise broiler chickens, a breed specifically developed for rapid growth and high meat yield, particularly in the breast and thigh areas. To ensure consistency in texture and flavor, the birds are typically grown under controlled feeding regimens with strict monitoring of their diet, environment, and health status from hatchery to harvest. Once the birds reach the appropriate weight and age, usually between 5 to 7 weeks, they are transported live in temperature-regulated, well-ventilated trucks to the processing facility. Upon arrival, the birds are unloaded through an automated conveyor system and transferred to a staging area that uses dim lighting and gentle sound cues to keep the animals calm. This pre-processing environment is crucial for maintaining meat quality, as high stress can cause conditions like pale, soft, and exudative meat, or dark, firm, dry meat, which are both unsuitable for KFC's strict quality requirements. The first critical step in the factory is stunning, which is done using controlled atmosphere stunning, a method that introduces carbon dioxide in gradually increasing concentrations to render the chickens unconscious. This technique is widely considered more humane and helps preserve the quality of the meat. Once the birds are unconscious, they move to the next stage, where an automated system makes a precise incision to the neck, ensuring rapid and thorough bleeding. The bleeding process is closely timed and monitored using sensors and timers to maximize the efficiency of blood removal, which is essential not only for meat appearance and shelf life, but also for meeting food safety regulations. Following exsanguination, the birds proceed through a high-capacity scalding tank filled with water heated to approximately 60 degrees Celsius. This stage loosens the feathers by relaxing the collagen in the feather follicles. The duration and temperature are controlled to a fine margin to ensure that the skin is neither overcooked nor damaged. After scalding, the birds are transferred into rotary feather pluckers, drum-shaped machines lined with soft rubber fingers that rotate at high speeds. These fingers remove feathers through a gentle abrasive action. Any residual feathers, particularly around the wings and tail, are removed by additional targeted plucking devices or hand finishing stations, depending on the processing line speed and factory setup. The next step is evisceration, a highly mechanized process involving robotic arms and vision-guided machinery. The system first makes a precise incision along the abdominal cavity before extracting the internal organs. This includes the heart, liver, gizzard, and intestines, which are separated into byproduct streams for different uses or disposal. Each carcass is inspected by high-speed cameras equipped with AI-powered image recognition software to detect any abnormalities such as bruising, discoloration, or contamination. Chickens that fail this inspection are automatically diverted from the production line for further examination or removal. This real-time quality assurance technology helps maintain a consistent and safe supply of chicken for further processing. Now it's time to move on to the chilling process, which is absolutely vital for halting bacterial growth and ensuring a clean transition from slaughter to further cutting and seasoning. KFC factories typically use an immersion chilling method where eviscerated chickens are conveyed through long stainless steel tanks filled with chlorinated cold water, maintained at around 0 to 4 degrees Celsius. The flow of water is designed in a countercurrent pattern, meaning the cleanest water contacts the most recently added chickens, ensuring optimal hygiene. This step rapidly reduces the internal temperature of the chicken from roughly 40 degrees Celsius to below 4 degrees within an hour, thereby locking in freshness and significantly extending the shelf life of the meat. After chilling, the carcasses proceed to the cutting and portioning stage. This part of the process is perhaps one of the most intricate in the factory. Specialized rotary cutting machines equipped with lasers and 3D scanners assess the size and density of each chicken in real time. Based on this data, programmable robotic blades segment the carcasses into uniform cuts: legs, thighs, wings, breasts, and keels. Each piece is sized to match strict dimensional and weight criteria, which are crucial for ensuring consistent cooking times and presentation across all KFC restaurants worldwide. The system is calibrated to yield the optimal number of each type of piece from every bird, reducing waste and maximizing efficiency. If a cut doesn't meet the precise size range, it is automatically redirected for use in alternative products like tenders or popcorn chicken. The next phase focuses on marination, a process that introduces moisture, flavor, and functional ingredients into the chicken to enhance both taste and texture. Once portioned, the chicken pieces are loaded into massive stainless steel tumblers, each capable of holding hundreds of kilograms of product. Inside the tumbler, a proprietary liquid marinade blend is introduced. While the exact formulation is a closely guarded secret, the marinade typically includes salt, phosphate-based tenderizers, flavoring agents, and sometimes buttermilk solids to create the tender, juicy interior that KFC is known for. The tumbling action lasts anywhere from 15 to 30 minutes, depending on the batch size and desired intensity, and the drum rotates on multiple axes to ensure that every surface of every piece of chicken is exposed to the marinade. This mechanical agitation also helps the meat fibers absorb the liquid more thoroughly, contributing to the product's juiciness even after high temperature frying. But up next comes the breading stage, which is arguably the most iconic part of KFC's production process. After marination, the chicken is gently drained and transferred to the breading stations, where each piece is coated in the proprietary blend of flour and seasoning known famously as the 11 herbs and spices. To replicate the hand-breaded quality that KFC is known for, even at industrial scale, specialized breading drums are used. These drums simulate the hand-tossing action by gently rolling the chicken pieces in the seasoned flour, while pneumatic paddles and vibration systems ensure that every crevice is fully coated. At this point, moisture content is carefully controlled to ensure adhesion without creating clumps or overly moist surfaces, which would ruin the crispy texture during frying. Once breaded, the chicken moves immediately to the par frying or pre-frying stage. This step is critical for setting the breading so it doesn't fall off during full cooking at the restaurant. The breaded pieces are passed through continuous fryers filled with hot oil maintained at temperatures between 170 to 180 degrees Celsius. In this stage, the chicken is fried for a short duration, usually 90 to 120 seconds, just enough to solidify the coating and begin the Maillard reaction, which is responsible for the development of flavor and the golden color. The oil used in this step is filtered and refreshed continuously using an inline oil management system that maintains optimal frying conditions and ensures that the final product is never tainted by burnt residues or off flavors. The partially cooked chicken is then lifted out of the fryer via a conveyor system and deposited onto a draining belt that uses both gravity and air jets to remove excess oil. Now, it's time to transition to the flash freezing process. This is where partially cooked chicken is rapidly frozen to lock in all the flavors, textures, and moisture absorbed during marination and breading. Each piece is conveyed into a spiral freezer or impingement freezer, both of which use sub-zero air blasts or liquid nitrogen vapor to drop the temperature of the chicken from over 60 degrees Celsius to below -18 degrees in under 10 minutes. Rapid freezing is crucial to prevent the formation of large ice crystals, which can damage the cellular structure of the meat and result in dryness or texture loss after final cooking. During this process, each piece is also individually quick frozen, which prevents clumping and allows for precise portioning when packaging. The next step in the factory process is the automated packaging of the individually quick frozen, par-fried chicken pieces, a phase that combines high-speed precision machinery with meticulous control over product integrity. Once the chicken emerges from the spiral or impingement freezer, each piece is conveyed to a sophisticated vision inspection system that performs a final quality assurance check. High-resolution cameras and laser scanners examine each piece for uniform breading coverage, appropriate size, and the absence of any structural defects like broken bones or irregular shapes. Pieces that fail this inspection are removed from the line using targeted air jets and routed for rework or disposal, depending on factory protocol. Once the pieces pass inspection, they are conveyed into a portioning station where intelligent weighing and sorting systems group them into standardized sets that align with KFC's iconic bucket meal configurations. These could be 8-piece, 12-piece, or 16-piece configurations, depending on the regional product lineup. Multi-head weighing machines calculate the total weight and count of each portion, ensuring that every pack not only meets visual and compositional standards, but also falls within a narrowly defined weight range for inventory accuracy and consistent customer experience. These grouping systems operate at incredibly high speeds, hundreds of portions per minute, with tolerances as tight as +1 gram. Each portion of chicken pieces is then dropped into a form-fill seal machine or into pre-formed plastic pouches, depending on the final packaging format. The form-fill seal machines shape a plastic film into a bag, load it with chicken, flush it with a nitrogen-rich gas to minimize oxygen, and heat seal it in a continuous, uninterrupted process. Modified atmosphere packaging is used here to extend shelf life while preventing freezer burn or flavor degradation. The gas blend, often a mix of nitrogen and carbon dioxide, inhibits microbial growth and oxidation without adding any chemicals or preservatives. After sealing, the packages are labeled with all necessary tracking and compliance information. High-speed thermal transfer printers apply labels that contain lot numbers, plant codes, production timestamps, and freeze dates. These labels also include data matrix barcodes or QR codes used for traceability, allowing KFC's central quality control teams to trace every package back to its exact farm, batch, and processing line in the event of a recall or audit. Automated verification systems scan each label for accuracy and readability. Any incorrectly labeled packages are automatically rejected from the line and placed in a designated review bin for manual inspection. Now it's time to move on to case packing, where multiple individually sealed packs of chicken are grouped into corrugated cardboard boxes, each built to withstand long-distance cold chain transportation. Robotic arms, equipped with vacuum suction grippers, pick and place the sealed bags into the boxes with extreme precision, ensuring that space is maximized while maintaining the integrity of the chicken. Each case typically holds a specific number of meals or bucket configurations and is marked with a unique identifier. Once filled, the boxes are sealed using automated taping machines and pass through weight verification stations to ensure each box matches the expected load. Once packed, these boxes are stacked onto pallets using robotic palletizers. These robots follow pre-programmed stacking patterns that balance weight and maximize vertical space without compromising stability. Slip sheets and corner boards are often inserted between layers to protect the boxes during transit. Each completed pallet is then shrink wrapped using a rotary arm or turntable stretch wrapper, which encases the entire stack in several layers of industrial plastic film to secure the load for transportation. A final barcode label is applied to each pallet, integrating it into the warehouse management system, which tracks every movement of inventory from production to dispatch. Next comes the crucial cold storage phase. The finished pallets are transferred via automated guided vehicles or high-speed conveyor systems into a massive cold storage facility, maintained at a consistent temperature of -18 degrees Celsius or lower. These storage facilities are designed with energy efficiency and inventory management in mind, often featuring high bay racking systems and vertical lift modules that allow for dense, organized storage. Temperature and humidity are monitored continuously by sensors linked to a centralized control room, where technicians receive alerts if any deviations occur. These warehouses are often equipped with backup generators and emergency protocols to ensure uninterrupted refrigeration in the event of power failures. After sufficient time in cold storage, which may range from a few days to several weeks depending on demand, the frozen chicken pallets are scheduled for distribution. The dispatch process begins with a pick and pack phase, where orders from various KFC regional hubs or franchise warehouses are collated. Advanced logistics software optimizes which pallets to pull based on freshness, production date, and delivery location. Selected pallets are loaded onto refrigerated trailers that maintain a controlled environment throughout the entire journey. These trucks use insulated walls and powerful refrigeration units that can be monitored remotely to ensure temperature compliance from factory to franchise. As these trucks transport the frozen chicken to regional KFC distribution centers or directly to individual restaurants, the cold chain is never broken. The receiving locations are equipped with cold storage facilities of their own, ensuring the chicken remains at safe temperatures until it's needed. At this stage, each restaurant receives a specific allocation based on forecasted customer demand, which is calculated using advanced demand planning software linked to point-of-sale data and regional market trends. The chicken remains sealed until it's ready to be used in the restaurant's kitchen, where the final stages of cooking take place. But now it's time to dive into the heart of the KFC restaurant kitchen, where the transformation from pre-cooked frozen chicken into the hot, crispy, golden brown pieces we all recognize occurs. After thawing in temperature-controlled refrigeration units for a specific number of hours, typically overnight, the chicken is brought to the breading station. Though the chicken was par-fried and breaded at the factory, a second layer of fresh breading is applied in-store to create the distinctive double crunch texture KFC is famous for. This is where the Colonel's proprietary 11 herbs and spices come into play. Each restaurant receives sealed tubs of this secret seasoning blend, pre-measured and tamper-proof. The thawed chicken pieces are first dipped into a cold, seasoned egg wash or a specialized batter mix, depending on the region. Then, they are placed into large breading bins containing the flour and spice mixture. Trained team members follow a specific press and fold technique, which involves pressing the flour onto the surface of the chicken and folding it multiple times to ensure full adhesion and the formation of the characteristic craggy, crispy coating. Each piece is then gently shaken to remove excess breading and laid out on wire racks to rest before frying. This resting period is short but essential. It allows the coating to set and adhere to the surface of the meat, reducing slippage during frying. Next, the chicken is placed into large open fryers filled with high stability frying oil, often a soybean or canola blend, optimized for high temperatures and neutral taste. The fryers are preheated to exact temperatures, typically around 170 to 180 degrees Celsius, and the chicken is cooked under pressure for a controlled duration. KFC's use of pressure fryers is a distinctive element of its cooking process. The pressure cooking not only reduces cooking time, but also seals in moisture, ensuring the chicken remains juicy while achieving a perfectly crispy exterior. Sensors inside the fryer monitor oil temperature, pressure levels, and cooking duration down to the second. Once the timer signals completion, the fryer basket lifts automatically and the cooked chicken is removed using heat-safe tools to ensure safety and hygiene. After frying, the chicken is transferred to heated holding cabinets that maintain a precise internal temperature, typically around 60 to 65 degrees Celsius, for a limited time, usually no longer than 90 minutes, to ensure optimal freshness and food safety. These cabinets are fitted with internal timers and alert systems to prompt kitchen staff when a batch is nearing the end of its holding time. Any product not sold within this window is discarded according to food safety protocols to maintain KFC standards. Now that the chicken is hot, crisp, and ready, it's portioned into the familiar red and white striped buckets. Each bucket is made from food-grade, grease-resistant cardboard, printed with high-resolution branding that remains vibrant, even under heat and oil exposure. The buckets are assembled on-site from flat-pack form using pop and lock mechanisms and lined with waxed paper liners. The kitchen crew follows strict guidelines when arranging the pieces inside each bucket, ensuring an appealing visual mix of drums, thighs, wings, and breasts. The buckets are then sealed with fitted plastic or cardboard lids to retain heat and are either handed to walk-in customers or packed into thermal delivery bags for transport. The final stretch of the production process involves a complex web of quality assurance protocols, food safety audits, sustainability initiatives, and continual technological improvements, all of which are critical to ensuring that every KFC fried chicken bucket, whether purchased in Tokyo, New York, or Johannesburg, meets the same high standard of taste, appearance, and food safety. These behind-the-scenes systems may not be visible to the end consumer, but they represent the foundation of KFC's global manufacturing and supply chain model. One of the most rigorous systems in place is the Hazard Analysis and Critical Control Points, or HACCP, framework. This is applied across all phases of the production lifecycle, from live animal handling at the poultry farms to final packaging at the restaurant level. Every critical control point is identified, monitored, and logged digitally. For example, in the chilling process, sensors verify that the internal temperature of chicken pieces drops to below 4 degrees Celsius within a very specific time frame. If any batch fails to meet that requirement, the system will automatically flag the anomaly, prevent further processing, and isolate the affected lot until a manual inspection is completed. These digital controls are complemented by human oversight. Trained quality control technicians regularly inspect samples at random, visually assessing breeding adhesion, meat color, texture, and aroma. At the plant level, sanitation is treated as a mission-critical activity. Every line, blade, and conveyor is cleaned on a strict schedule using a validated multi-step process that includes rinsing, application of food-grade alkaline and acidic detergents, hot water sanitizing, and ATP testing to detect any microbial residues. Cleaning in place systems are used in closed-loop systems like marinade blenders and oil filtration units, ensuring deep sanitation without the need for dismantling complex machinery. Swabs are taken from surfaces and air samples collected to detect airborne pathogens, all analyzed in on-site microbiological labs. If even a trace of Listeria, Salmonella, or E. coli is detected, entire zones of the plant are shut down and sanitized before production can resume. In parallel to these food safety systems, sensory panels and culinary scientists at centralized R&D hubs conduct organoleptic tests to ensure product consistency. These tests assess everything from the crunch of the breading to the juiciness of the meat and the aroma released when the bucket is first opened. Chicken from multiple plants is cooked and compared side by side in blind taste tests to identify deviations in flavor or texture. If a factory's output strays from the baseline profile, its formulations and techniques are reviewed. In some cases, regional adaptations are permitted. For instance, a slightly spicier breading formula in Southeast Asia, or a less salty blend in Scandinavian markets. But these must be approved through corporate sensory panels and extensive pilot runs. Now it's time to take a look at how traceability and supply chain visibility are achieved at scale. Every piece of chicken can be traced through a blockchain-based system that logs data from farm to fryer. RFID tags and barcode labels track each pallet, batch, and case throughout its journey. When a truck departs a cold storage warehouse, its GPS location is monitored in real time, and its refrigeration status is transmitted back to the operations center every 5 minutes. If a delivery truck's temperature rises above the acceptable range for more than 10 minutes, alerts are sent automatically, and corrective actions are triggered, either rerouting to a nearby cold facility or discarding the load, depending on the severity of the excursion. Once the product reaches the restaurant, the store-level staff become the final link in the quality chain. Every team member is trained not just in food preparation, but in safe handling and equipment calibration. They measure oil temperatures with infrared thermometers before every cooking cycle, check holding cabinet thermostats each hour, and perform timed inventory rotations to prevent expired stock from being used. Any discrepancies are flagged in a digital checklist that is reviewed daily by shift supervisors and weekly by regional managers. Corporate auditors also perform unannounced inspections using checklists derived from international food safety certifications such as ISO 22000 and BRC Global Standards. But up next is a growing area of emphasis for KFC's manufacturing process, sustainability. As environmental concerns increasingly shape consumer expectations and regulatory policy, KFC and its supply chain partners have invested heavily in reducing their environmental impact without compromising efficiency or food safety. For instance, many factories now operate on hybrid energy models that integrate solar or wind power into the grid supply. Heat exchangers capture and recycle waste heat from fryers and ovens to preheat water for cleaning cycles. Water treatment plants have been installed adjacent to major facilities to purify and reuse water from scalding tanks and chilling baths, thereby reducing freshwater consumption by up to 60%. Waste management is another cornerstone of sustainable operations. Offcuts, bones, and organ meats removed during the evisceration process are rendered into protein meal for use in animal feed or fertilizer. Oil used during the par frying phase is filtered multiple times and eventually recycled through third-party processes into biodiesel or industrial lubricants. Even the breading flour that falls off during coating is collected, sifted, and reused within the same batch cycle if it remains uncontaminated thanks to high-speed sifters and air classification systems. Packaging materials are continuously redesigned to reduce plastic use, and many regional markets have adopted compostable or recyclable buckets made from sugarcane fiber or recycled cardboard. Now let's touch on automation and the future of food manufacturing. KFC's supply chain continues to push the boundaries of factory automation. Smart robotics now handle everything from chicken loading and cutting to box folding and pallet stacking. Machine learning algorithms analyze yield patterns, worker performance, and maintenance schedules to optimize output while minimizing downtime. Vision systems are paired with artificial intelligence to assess product quality in real time, not just based on weight and shape, but also by identifying anomalies invisible to the human eye, such as microfractures or uneven breading density. One of the most promising developments is the integration of digital twins, virtual replicas of entire production lines that allow engineers to test modifications in real time before applying them in physical factories. If a new breeding formula is under development, it can be modeled digitally to predict how it will behave under tumbling, par-frying, and freezing conditions. These simulations save weeks of trial and error testing and reduce waste. Some facilities even employ predictive maintenance systems powered by sensors embedded in critical equipment. These sensors monitor vibration, temperature, and pressure, allowing for preemptive repairs before machinery fails, ensuring smooth operations and uninterrupted chicken production. KFC has also begun exploring vertical integration of its logistics chain. In some regions, specially designed micro-factories are situated closer to major urban centers, reducing transit time and carbon emissions. These micro-factories handle final stage breading and par-frying, enabling fresher product delivery and enhanced responsiveness to demand fluctuations. Combined with real-time sales analytics from thousands of KFC restaurants, these decentralized production nodes can respond dynamically, ramping up or down based on foot traffic, promotions, or seasonality. The manufacturing process for Ruffles potato chips begins long before a potato even enters the production facility. It starts with agricultural planning and controlled sourcing. Ruffles, as a brand under Frito-Lay, utilizes proprietary potato varieties that are cultivated specifically for chip production. These aren't the same types of potatoes used for baking or mashing. Instead, Frito-Lay contracts with dozens of partner farms across the United States and other regions to grow chipping potatoes, varieties like Atlantic, Snowden, or proprietary Frito-Lay hybrids that are selected for their specific characteristics: high dry matter content, low sugar levels, uniform shape, and dense texture. Each crop is grown with tight controls on irrigation, fertilizer use, and harvesting schedules to ensure consistency and minimize storage degradation. Potatoes that are too moist, sugary, or irregular in shape would result in chips that are oily, dark, or fragile, none of which meet the Ruffles brand standard. At harvest, potatoes are collected using automated harvesters equipped with rubber conveyors that minimize bruising. They're loaded into transport trucks and sent to the factory, often within a few days of being pulled from the ground. When the potatoes arrive at the processing plant, they enter the facility through the raw receiving bay. These are enclosed intake areas where truckloads are weighed, logged, and tested before being accepted for processing. At this point, technicians from the quality assurance team extract random samples from the load to check for size uniformity, sugar content, starch levels, and moisture content. Any batch of potatoes that falls outside the tight specification window may be rejected or diverted to other non-chip product lines. Once cleared, the potatoes are offloaded from the trucks into a large receiving pit, essentially a hopper connected to a series of conveyor belts. From here, the potatoes are moved toward the initial cleaning phase. This begins with the destoning drum. As the potatoes enter this large rotating cylinder, jets of water and the rotating action cause heavier materials, like rocks or clumps of soil, to separate and fall through grated bottoms. Potatoes are lighter and are lifted to the next stage. From the destoning drum, the potatoes enter the pre-wash flume system. A flume is a water-filled channel that moves product gently using the flow of water instead of belts. This minimizes physical damage to the raw potatoes while removing dirt and loose debris. The flume water is treated and recirculated through industrial filters and chemical dosing systems to ensure both sanitation and water conservation. In many modern plants, the water used in these systems is part of a closed-loop recovery system designed to reduce environmental impact. The next stop is the rotary scrubber. This is a long, cylindrical machine fitted with internal brushes that rotate as the potatoes pass through. High-pressure nozzles spray water as the tub rotates, scrubbing away any remaining mud, sand, or biological debris. The inside of the scrubber is lined with abrasive surfaces that help clean the rough skin of the potato without cutting into the flesh. The goal here is to deliver a clean, undamaged potato with its skin still intact, ready for inspection. After scrubbing, the potatoes are lifted out of the washer by a cleated incline conveyor and passed through a visual and automated inspection system. In this phase, both human inspectors and camera-based vision systems work in parallel. The conveyor belt is engineered to spread out potatoes into a single layer, and each tuber moves past a combination of high-resolution cameras and infrared sensors. These systems are trained to detect green spots, bruises, cuts, or signs of rot. Any substandard potatoes are rejected via automated diverter arms or air jets, which remove the faulty items from the belt and send them to waste or compost streams. Human operators stationed along the line also remove visibly defective items that machines might miss, such as those with odd shapes that won't slice well on the crinkle-cut blades. Every removed potato is scanned and logged into the factory's waste tracking system, allowing operators to identify trends and address upstream sourcing problems if too many rejects appear from a single truckload. Now that the potatoes have passed visual inspection, they move on to the peeling station. For Ruffles, peeling is essential. While some gourmet-style chips retain their skins, Ruffles chips require a smooth, peeled surface to produce clean, consistent ridges during slicing. Peeling is achieved using a combination of steam and abrasion in what's known as a steam peeler. The steam peeler is a high-pressure vessel that receives a batch of potatoes, seals the chamber, and subjects the potatoes to pressurized steam, usually around 180-220 psi for 8 to 20 seconds. This superheated environment rapidly loosens the outer skin layer by partially gelatinizing the pectin between the skin and the underlying tissue. Once the steam cycle ends, a sudden pressure drop causes the skin to puff and detach slightly from the flesh. Immediately after this, the potatoes are discharged into an abrasive roller peeler. This is a rotating drum lined with rough surfaces, often embedded with carborundum grit, that gently scrubs the now loosened skins away. Water sprays are used to flush away the skins and clean the exposed potato surface. The amount of skin removed is carefully monitored. Too much abrasion would remove usable flesh and increase waste. Too little would leave patches of skin that affect the slicing process. The peeled potatoes are rinsed again in chilled water to stop any residual thermal activity and prevent enzymatic browning. A small dose of food-safe antioxidant, like sodium metabisulfite or citric acid, may be added to the rinse water to preserve the pale color of the peeled surface and prevent discoloration before slicing. At this stage, the potatoes are fully clean, peeled, and ready for their signature transformation, being cut into the iconic ridged slices that define a Ruffles chip. With the freshly peeled and rinsed potatoes now ready for transformation, the next phase in the Ruffles production process focuses on slicing, the moment where whole tubers are precisely cut into their distinctive ridged form. The ridges are far more than a visual or marketing detail. They play a critical role in the chip's strength, texture, and frying performance. This stage involves advanced slicing technology, careful temperature and starch control, and continuous monitoring to ensure each slice is the exact thickness, shape, and structural consistency required for optimal cooking and crispness. The peeled potatoes are transported to the slicing area via gentle, water-based flumes or soft conveyor belts to minimize impact and prevent bruising. Once they reach the slicing units, the potatoes are fed one by one into high-speed rotary slicers designed specifically for crinkle or corrugated cuts. These industrial slicing machines use a rotating impeller or feed wheel to press each potato firmly against a stationary, razor-sharp cutting head fitted with ridged blades. The blades are precisely machined to form a consistent wave pattern, typically with a wave amplitude of 1.5, 2.5 mm and a thickness of around 1.3, 1.5 mm. Unlike flat chip slicing, where a smooth blade is sufficient, ruffles require a carefully engineered ridged blade made of hardened stainless steel. These blades are aligned at specific angles to produce even, undistorted waves along the chip's entire surface. The sharpness, speed of rotation, and pressure exerted must be perfectly balanced. Too much force or misalignment can result in chips with uneven ridges or broken tips, which would either fry unevenly or be rejected later during inspection. The sliced potatoes are ejected from the slicing drum at high velocity and collected in a shallow trough or on a belt that immediately begins the next critical step: starch removal and surface moisture control. Every potato contains natural starch, and when sliced, a large amount of that starch is released onto the cut surfaces. If not removed, this surface starch can interfere with the frying process, causing chips to stick together, fry unevenly, or develop burnt spots. It can also result in a greasy or gummy mouthfeel, which is unacceptable for Ruffles' clean, crisp texture. To remove excess starch, the slices pass through a multi-stage rinsing system. In the first phase, they enter a flume filled with cold, recirculated water, where they are gently agitated to dislodge free starch. The water in this flume is constantly filtered and monitored for starch content, with automated control systems adjusting flow rate and replacement intervals to maintain effectiveness. Following the first rinse, the slices often move through a series of cascading rinse curtains, sheets of filtered water that fall like waterfalls over the slices as they travel along a mesh or perforated conveyor belt. This helps remove residual starch without applying any mechanical force that could break the delicate ridges. After rinsing, the slices must be dried to a specific degree, not fully desiccated, but dry enough on the surface to allow the hot oil in the fryer to crisp the exterior without creating steam pockets or excessive foaming. This is achieved using a dewatering shaker and an air drying tunnel. The dewatering shaker is a vibrating belt or tray that shakes the slices gently to remove bulk water. The slices then pass under high-velocity air knives, rows of precisely aligned jets that blast room temperature or slightly warmed air across the chip surface. The air knives are tuned to create a shearing effect that strips away surface moisture while maintaining the shape and integrity of the ridged cuts. At this point, the slices are considered ready for frying, but only if they meet one final set of pre-cook inspection criteria. Before entering the fryer, the slices pass through an optical sorting system. This state-of-the-art inspection station uses a combination of high-resolution cameras, infrared sensors, and sometimes laser scanners to detect defects such as green spots, bruising, overly large slices, or broken pieces. Defective slices are rejected with microbursts of compressed air, which knock them off the main conveyor line and into waste or reprocessing bins. The acceptable slices, meanwhile, are evenly distributed across the width of the fryer in feed conveyor to ensure uniform exposure to hot oil. Frying is where the raw slices become what we recognize as potato chips. And for Ruffles, this step is both art and engineering. The chips are fried in continuous fryers, long stainless steel troughs filled with high-temperature cooking oil. The oil is typically a carefully formulated blend of vegetable oils, often including sunflower, corn, or canola oil, chosen for their high smoke points, neutral flavor, and oxidative stability. The oil is filtered, treated, and replaced on a tightly regulated schedule to maintain quality and avoid flavor degradation. As the slices enter the fryer, they are immediately submerged by a submersion conveyor that ensures they stay evenly beneath the oil's surface throughout the cooking process. The oil is maintained at a precise temperature, usually between 170 degrees Celsius and 190 degrees Celsius. This range is critical. Too cool, and the chips absorb oil and turn soggy. Too hot, and they brown too quickly or develop burnt notes. Each chip is cooked for approximately 2 to 3 minutes, depending on thickness, oil composition, and desired moisture content. Inside the fryer, the chips expand slightly and crisp as their internal water content rapidly evaporates. The ridged surface of Ruffles causes the chip to fry unevenly by design, creating micro variations in texture that result in a more substantial bite and greater structural integrity. The ridges also slow oil drainage, allowing a slightly longer dwell time that contributes to the chip's durability and resistance to breakage during dipping. The fryer is equipped with multiple sensors and flow meters that measure oil temperature, turnover rate, chip feed rate, and even in-oil moisture concentration. These data are analyzed in real time by the factory's central control system, allowing operators to make immediate adjustments. In many facilities, the frying process is linked to upstream slicing sensors. For example, if slightly thicker slices are detected coming from the cutter. The fryer conveyor speed is slowed accordingly to ensure proper cook time. As the chips emerge from the fryer, they pass through an oil draining phase. A vibrating conveyor with a perforated surface allows excess oil to drip off. This is immediately followed by an air cooling system that begins to lower the chip's temperature, halting further cooking and locking in texture. Cooling is essential not only for texture stability, but also to prepare the chips for seasoning, which happens shortly after. But before we get to seasoning, there's a critical interlude in the process: moisture analysis and inline quality control. At this stage, a small percentage of chips are diverted through a sampling chute to a nearby test station. Here, technicians use moisture analyzers, color meters, and even acoustic crispness testers to evaluate product characteristics. These tests ensure that the chips meet the factory's targets for final moisture content, color uniformity, and physical integrity. As the freshly fried and cooled Ruffles chips exit the fryer and pass through preliminary quality control, they enter one of the most dynamic and highly controlled stages in the factory: seasoning. This is the phase where the chips receive their final flavor identity, whether it's the original lightly salted variant, sour cream and onion, cheddar and sour cream, jalapeno ranch, or any of the other regional and seasonal flavor options Ruffles is known for. Applying these flavors evenly, consistently, and at high speed while preserving the chip's structural integrity and minimizing waste is a challenge that modern factories solve using specialized equipment and real-time process monitoring. The chips arrive at the seasoning station on a wide, inclined conveyor or vibratory tray that serves two main functions. It spreads the chips out into a single layer to prevent overlap, and it gently agglomerates chips to control their flow into the seasoning drum without damaging them. Due to the ridged shape and the thicker cut of Ruffles compared to standard potato chips, seasoning application must account for deeper surface area and variable orientation. Some chips will face ridge side up, some down, some angled. Seasoning application takes place inside a rotating tumbler drum, also called a flavor drum or seasoning cylinder. This stainless steel drum is set at a slight incline and constantly turns on its horizontal axis, gently lifting and tumbling the chips while they rotate through it. At the entrance to this drum, a continuous metered flow of seasoning powder is dispensed through an auger-based dosing system. The seasoning blend, pre-mixed according to a proprietary formula, includes a combination of salt, natural, and artificial flavorings, cheese powders, dehydrated dairy, onion and garlic powders, spices, yeast extract, and anti-caking agents. The dosage rate of the seasoning is tightly controlled via real-time feedback systems. Optical sensors measure the chip volume entering the drum, and the dosing screw adjusts the delivery rate to maintain an ideal flavor to surface area ratio. Too much seasoning leads to clumping, oversalted chips, and waste. Too little results in bland or unevenly flavored chips that fail quality checks. For cheese-based seasonings, which are more moisture sensitive, the flow system may include a nitrogen-purged hopper or desiccant units to prevent clumping in humid environments. Inside the flavor drum, fine misting nozzles also spray a light coating of oil to help the seasoning adhere evenly to the chip surface. This atomized oil does not soak the chips, but rather creates a microfilm that holds the powder in place without compromising crunch. The rate of oil application, angle of spray, and temperature are all adjusted based on the type of seasoning used. For example, heavily coated varieties like cheddar and sour cream require more binder oil and a slightly longer tumbling duration to ensure every chip is fully and evenly coated. Throughout the seasoning process, line operators and quality assurance technicians take random samples every few minutes. These samples are assessed for seasoning coverage, color intensity, and surface powder levels. In more advanced factories, seasoning uniformity is checked with hyperspectral cameras that scan the chips as they exit the drum, detecting variations invisible to the human eye and triggering alerts or auto-calibration if inconsistencies are detected. Once the chips have been properly seasoned, they are transferred to the packaging phase. This is a highly automated and synchronized system that must meet several objectives simultaneously. Protect the chips from breakage, preserve freshness, prevent contamination, provide product information to the consumer, and maintain traceability for safety audits. Packaging begins with product accumulation. Conveyors from multiple seasoning drums may feed into a single accumulation hopper or weigher, depending on line configuration. This hopper temporarily holds chips before they're dispensed into individual bags via a multi-head combination weigher. A multi-head weigher is an advanced piece of equipment with multiple radial feed hoppers arranged in a circular pattern. Each hopper releases a small portion of chips, and a central computer instantly calculates which combination of hoppers adds up closest to the target weight, say 28.3 grams for a single serve bag. This combination is released simultaneously into a timing hopper, which drops the exact weight into a vertical form-fill-seal packaging machine. The VFFS machine forms bags from a continuous roll of printed plastic film, often made from multi-layer laminate materials with barriers against oxygen, light, and moisture. As the chips drop from the weigher into the forming tube, the film is pulled around the tube, sealed lengthwise, and sealed again at the top and bottom with heated jaws, creating a pillow-style bag. Before the top seal is made, a precise dose of nitrogen gas is injected into the bag, a process known as nitrogen flushing. This replaces the oxygen-rich air inside the package to reduce oxidation, extend shelf life, and protect the chips from crushing by slightly inflating the bag. Once sealed, each bag moves through a print station where batch codes, production time, plant ID, and expiration dates are applied using inkjet or thermal printers. Bags then pass through check weighers to confirm accuracy. Any bag outside the designated weight window is automatically rejected and diverted to a rework bin. Metal detectors or X-ray systems scan every bag to ensure no foreign objects have entered the product during processing. This is standard for all snack food production and a critical part of food safety compliance. From there, the sealed and verified bags are grouped into cartons or display trays by robotic case packers. These cartons are sealed with tape or glue and labeled with barcodes and tracking information. Finally, cartons are stacked onto pallets by robotic palletizers, often using suction cup grippers or clamp arms to gently stack without damaging contents. Pallets are wrapped in stretch film and staged in the finished goods warehouse, which is climate controlled to preserve chip texture and flavor. At every point along this packaging line, sensors, programmable logic controllers, and SCADA systems monitor performance metrics, line speed, reject rates, weigher accuracy, sealing temperature, film feed rate, and more. Maintenance logs and process trends are analysed weekly to identify emerging issues, improve throughput, and reduce product loss. Beyond the physical movement of chips, there are strict sanitation and allergen management systems in place. Since some Ruffles flavors may contain milk, cheese, or other allergens, production lines must be deep cleaned between flavor runs. Clean in place protocols involve dismantling sections of the line using high-pressure washdowns, food-safe detergents, and microbial swab testing. Detailed records of every cleaning cycle are logged and audited regularly. In addition to cleaning, factories must manage cross-contamination risk during flavor changeovers. This includes running purge batches, segregating flavoring agents in separate storage silos, and using dedicated feed lines wherever possible. Every batch of Ruffles is linked back to a full traceability profile, covering raw material lot codes, equipment used, line operator IDs, and environmental conditions during processing. As the freshly packaged Ruffles chips leave the main production floor, the final phase of manufacturing comes into focus. A sophisticated web of logistics, sustainability efforts, continuous process optimization, and digital innovation. While the chips themselves are complete, the factory does not pause. Instead, a parallel system of data analysis, quality assurance, and supply chain orchestration continues operating in the background, ensuring the product not only meets current demand, but evolves to meet future expectations. These behind-the-scenes processes are integral to the long-term efficiency, environmental responsibility, and market success of Ruffles. At the heart of these operations is a factory-wide data infrastructure that tracks every input and output, from raw potatoes to finished pallets. Each batch of Ruffles produced is logged into an integrated manufacturing execution system. This software records the origin of each ingredient, the time and conditions of each processing step, the performance of every machine along the line, and even environmental metrics like room humidity and oil turnover frequency. The MES integrates with enterprise resource planning systems, providing real-time visibility into inventory levels, sales forecasts, and raw material consumption. This data is not merely archived, it's analyzed continuously using advanced analytics platforms and AI-based algorithms. These systems look for patterns in machine downtime, chip reject rates, oil consumption per batch, or seasonal fluctuations in potato solids. If a fryer begins to show a subtle increase in oil absorption, or if seasoning coverage becomes slightly more variable, the system flags it. Maintenance crews and process engineers receive alerts and can intervene before the issue affects product quality or efficiency. Predictive maintenance models also help avoid equipment failure by identifying when motors, pumps, or slicers are approaching wear thresholds. One of the key areas of focus in modern Ruffles factories is oil management. Frying oil is both a major cost and a major variable in product consistency and sustainability. The oil in the continuous fryer is constantly recirculated through filtration units that remove chip fines and particulates. Inline sensors monitor the free fatty acid content, color, and total polar materials in the oil, 3 indicators of oil degradation. When these metrics exceed defined limits, the system initiates partial or full oil replacement protocols. Some facilities have implemented smart fryer systems that dynamically adjust oil flow and heat profiles based on chip load and moisture level, significantly reducing oil turnover without compromising flavor or texture. Environmental sustainability is another priority embedded into Ruffles manufacturing. Frito-Lay, the parent brand, has committed to reducing water, energy, and greenhouse gas emissions across its snack food plants. One way this is achieved is through water reclamation. The flume water used to transport, wash, and rinse potatoes is filtered, UV treated, and reused multiple times before final disposal. Similarly, the steam peelers are equipped with condensate recovery systems that recycle steam condensate back into the boiler system, conserving energy and reducing water use. Electricity usage is optimized through variable frequency drives on conveyors and pumps, while LED lighting, motion sensors, and insulated cooling tunnels help minimize unnecessary energy waste. Some Ruffles production plants are now partially powered by renewable sources, including solar panels and biogas captured from on-site food waste digesters. Waste heat from fryers is recovered using heat exchangers and used to preheat incoming wash water, further boosting energy efficiency. Waste management is another crucial part of the factory's operations. Trimmings from biscuit cuts, chips rejected for size or overcooking, and seasoning overage are all collected, logged, and sent to animal feed processors or converted into biofuel when food safety protocols allow. Even the excess oil removed during de-oiling phases is collected, filtered, and sold to biodiesel manufacturers. Packaging materials are optimized for minimal plastic use, and packaging engineers continuously evaluate new laminates that offer better barrier performance with reduced environmental impact.